What if the universe had ignited just a fraction hotter at its birth? That tiny difference could have rewritten everything, altering the formation of galaxies, reshaping the chemistry of existence, and even deciding whether life as we know it could ever emerge. At the heart of this cosmic what-if lies a hidden blueprint, one that dictates how stars burn, how planets evolve, and how the forces of the universe weave reality together. But what if those forces had taken a different path? Would time itself feel the same? Would dark matter behave differently? Would intelligent life still rise? Or would something entirely unrecognizable take its place? At the very beginning of the universe, during what we call the Big Bang, temperatures were unimaginably high, far beyond what we can easily comprehend. Imagine the heat of 1 billion suns compressed into a tiny space, creating an environment where energy and matter behaved in extreme ways. If we were to imagine a tiny increase in temperature, even just a fraction of a percent, the consequences could be significant. This small increase might seem trivial, but in the context of the early universe, it could have triggered dramatic changes. For instance, the formation of fundamental particles such as quarks and electrons would occur differently. Colored quarks would start to combine to form protons and neutrons, influencing the balance between matter and antimatter, and potentially determining the universe's eventual structure. As the universe expanded and cooled, a rise in temperature on this scale could influence the formation of the first atomic nuclei during an era known as nucleosynthesis. If the temperature rose just a bit, it could lead to a greater abundance of certain elements, like helium, or even heavier elements, impacting the makeup of stars later in cosmic history. Moreover, cosmic inflation, a rapid expansion of the early universe, could also be affected. A slight temperature increase might enhance this expansion or lead to instabilities that could ripple through space-time. These changes could pave the way for the universe to evolve differently, perhaps altering the rate at which galaxies formed or the structure of large-scale formations we observe today. Thus, while seemingly minor, a tiny temperature shift at the dawn of the universe could unleash a cascade of cosmic events, shaping not just the early structure of matter, but also the entire fabric of our universe. In the universe's earliest moments, shortly after the Big Bang, it was an extremely hot and dense environment. Imagine a fantastically energetic soup where every particle was bouncing around wildly due to immense heat. During this time, energy was not evenly spread out. Instead, it was densely packed, and temperatures soared to levels that are hard to comprehend. As the universe started to expand, like a balloon being blown up, this energy began to disperse. This cooling process led to significant changes in how particles formed. Initially, the energy was so high that it couldn't even combine to form stable particles. Instead, it constantly rained down pairs of particles and their counterparts, like electron and positron pairs. These pairs appeared and vanished in a flash, symbolizing the chaotic nature of that early universe. As the universe continued to cool, the energy level dropped enough for more stable particles, such as protons and neutrons, to emerge from this energetic mix. These fundamental building blocks began to form atoms, primarily hydrogen and helium. This transition marked a critical point in cosmic history, where instability turned into the formation of matter. The once chaotic scene began to settle into the more structured universe we see today. The distribution of energy also played a crucial role. Rather than being uniform, it created fluctuations or variations in density. These slight differences were essential. They eventually became the seeds for galaxy formation. Regions with higher density attracted more matter, while less dense areas became voids. Thus, the universe's earliest moments set the stage for the complex cosmic structures we see billions of years later. A slight increase in temperature can set off a series of intriguing changes at the level of subatomic particles. When matter is heated, its particles, including atoms and their components, gain energy and begin to move more vigorously. Imagine a group of people in a room. When they start to feel warm, they become more active and less still. This added energy can cause particles to collide more frequently and with greater force. As these particles interact, they may undergo reactions that change their arrangement or state. For instance, if the temperature rise is significant enough, it could cause electrons to be ejected from atoms, leading to the formation of ions. This process alters the overall charge balance of the material, potentially affecting its chemical properties. Further reactions may occur as these newly freed particles engage with others. They could trigger a cascade of events, like the creation of more reactive ions or the acceleration of chemical reactions that were dormant at lower temperatures. For example, if this happens within a gas, the increased energy can lead to a greater frequency of collisions, increasing the likelihood of forming new compounds or breaking existing bonds. Moreover, in particle physics, a tiny temperature increase in a high-energy environment could even produce new particles through interactions involving energy conversion, thanks to the principles of mass-energy equivalence. Think of it like a small tremor in a fault line that might set off a larger earthquake. The initial change can have far-reaching effects, leading to the creation of entirely new entities in the particle arsenal. A small rise in temperature among subatomic particles acts as a catalyst for enhanced movement, increased collisions, and a wave of subsequent reactions, potentially resulting in new substances, changed states, or even new particles, all stemming from that initial nudging of energy. Cosmic inflation refers to the rapid expansion of the universe that occurred just after the Big Bang. In a way, you can think of this moment as the early universe stretching like an elastic band. Now, if we introduce a hotter environment into this scenario, the dynamics could change significantly. When the universe is hotter, it contains more energy. This increase in energy can affect particles and forces within the universe, potentially speeding up their interactions. If these particles collide with greater energy, they may influence the rate of expansion. A hotter environment might cause inflation to occur more quickly, leading to a faster expansion of space itself. The fabric of the cosmos would be stretching more vigorously. Moreover, changes in temperature can alter the characteristics of the fundamental forces. For example, conditions might favor different phases of matter or even the behavior of fields responsible for driving inflation. Such shifts could introduce unpredictability into the expansion process, possibly leading to dramatic changes in how the universe evolves. The inflation could become more erratic, causing varied rates of expansion in different regions, which offers a fascinating glimpse into how our universe's initial conditions impact its long-term fate. The Big Bang, often described as the universe's explosive beginning, set the stage for everything we see today. If the Big Bang had been just a little hotter, it would have impacted the very fabric of our universe, particularly the fundamental constants that govern how particles and forces behave. Think of these constants as the rules of a game. If the rules change even slightly, the game itself can play out in dramatically different ways. At a higher temperature during the Big Bang, particles would have moved faster and interacted more energetically. This intense environment could have allowed different particles to be created more readily. For instance, particles that would normally be rare might become more common. Imagine stirring a pot of soup. If you make it hotter, the ingredients mix differently and new flavors can emerge, influencing the overall dish. Additionally, the balance between different forces like gravity and electromagnetism could shift. These forces are dictated by constants, and if the initial conditions altered, it might lead to a universe where atoms form differently, stars ignite under different conditions, or even life as we know it might not emerge at all. These fundamental constants help dictate how atoms come together to form molecules, and how those molecules interact to create the complex structures, from galaxies down to the very life forms on Earth. Therefore, a marginal change in the temperature at the dawn of time holds the potential to create an unrecognizable universe, one that could behave in ways we cannot currently imagine. Each adjustment leads to different pathways of formation and evolution, ultimately influencing everything about the cosmos we observe today. The process of primordial nucleosynthesis refers to the formation of the lightest elements in the universe, primarily during the first few minutes after the Big Bang. During this time, the universe was incredibly hot and dense, allowing protons and neutrons to collide and combine to form the simplest elements like hydrogen, helium, and traces of lithium. If the heat levels of the early universe were altered, it could have significant effects on these nucleosynthesis processes. For instance, if temperatures were higher than observed, it would increase the energy available for nuclear reactions. This might lead to a greater production of helium and a different ratio of elements being formed. Conversely, if the temperatures were lower, nuclear reactions might occur less frequently or not at all, resulting in fewer light elements. This shift in the balance of elements would ultimately influence the composition of stars and galaxies, affecting everything from star formation to the types of heavy elements created in later stages of stellar evolution. The temperatures of the early universe play a crucial role in determining the fundamental building blocks of matter. Any significant change in heat levels would ripple through the cosmos, leaving a lasting imprint on the elements we see today. Understanding these dynamics helps scientists grasp not only the nature of the universe's origin, but also its ultimate fate. If the early universe had been just a bit hotter, the formation and life cycle of stars would be significantly altered. In the beginning, the universe was filled with a dense fog of gas and dust. Temperature plays a crucial role in the behavior of these materials. A hotter environment would mean that particles would move faster and collide with greater energy. This increase in temperature would lead to enhanced nuclear reactions. When clouds of gas began to collapse under their own gravity to form stars, a hotter beginning could accelerate this collapse. Stars might begin to form more quickly and become larger than they would in a cooler scenario. Larger stars burn more brightly and quickly, living shorter lives but ending in spectacular explosions known as supernovae. This means that the variety of stars we see today, along with the elements produced from these massive explosions, would be different. Additionally, the higher energy environment could affect how stars interact with their surrounding material throughout their life cycles. More energetic stars could lead to more intense stellar winds and a higher rate of material ejection into space. This material would enrich the interstellar medium with heavier elements at a faster pace, potentially altering the chemical pathways for future generations of stars and planets. Overall, a hotter beginning would create a different landscape for star formation, leading to a universe filled with stars that are either larger or born at different intervals. The entire cycle of stellar evolution would shift, influencing everything from the elemental composition of galaxies to the types of planets that could form around these stars. In the early universe, temperatures were incredibly high, reaching levels that allowed matter to exist in a hot, dense state. As the universe expanded, it cooled, leading to the formation of atoms and eventually galaxies. Temperature plays a crucial role in the physics of the early universe. When it was hotter, energy levels were higher, leading to rapid particle interactions and the formation of more massive structures. If we consider a scenario where the universe cooled more slowly than it actually did, we might see fewer lighter elements like hydrogen and helium forming. These are the building blocks of stars and galaxies. A more gradual cooling would allow for more time for complex structures to form, potentially resulting in a greater variety of galaxies. Conversely, if the universe cooled too quickly, only fewer, smaller galaxies might emerge, as the necessary conditions for their formation would not be met. Temperature affects the way matter clusters under gravity. Higher temperatures increase the energy and motion of particles, which could lead to higher density regions forming more rapidly, creating more galaxies. As galaxies are born, the interactions between these galaxies are also influenced by temperature. A hotter universe at an earlier stage might see dense clusters of galaxies forming, whereas a cooler early universe would lead to a more uniform distribution of galaxies with different characteristics. Overall, the temperature changes in the early universe are intricately tied to the types and abundance of galaxies formed. Warmer conditions may foster diverse and numerous galactic formations, while cooler scenarios could limit the complexity of the structures created. Understanding these dynamics helps us unravel how our universe has evolved over billions of years. When we consider altered star formation processes, we open the door to a range of unique and unfamiliar celestial phenomena. Start by imagining how stars typically form. They begin as clouds of gas and dust that collapse under their own gravity. If this process changes, perhaps due to increased turbulence from nearby supernova or the influence of other massive stars, we could see different outcomes. One possibility is the formation of very massive stars. Under certain conditions, gas clouds may funnel together more efficiently, leading to stars that are significantly larger than we currently see. These enormous stars burn hotter and faster than their smaller counterparts, ultimately resulting in powerful supernova explosions when they reach the end of their life cycle. The light and energy from these events can affect surrounding regions, potentially igniting further star formation or even leading to the creation of exotic objects like neutron stars and black holes. Another fascinating outcome could be the formation of binary or even triple star systems. In typical scenarios, stars form alone, but in altered environments, they might be born in clusters. If stars form close together, gravitational forces can bind them into pairs. These systems can create complex interactions, including dramatic flares, energy exchanges, and even the occasional collision, leading to spectacular cosmic displays. An unusual phenomenon that could emerge is the creation of failed stars, often called brown dwarfs. They are larger than planets but failed to ignite nuclear fusion in their cores. If star formation is interrupted or limited due to environmental factors, like lacking enough material, we could see a rise in these mysterious objects. Brown dwarfs are intriguing because they can emit energy and heat like stars, but without shining brightly in the same way. Further, alterations in the birth process of stars could lead to unexpected elements in their composition. Stars produce heavy elements through fusion, and if stars form with different materials or conditions, they might yield novel elements or isotopes. This variation could enrich the surrounding space with new chemistry, influencing the development of planets and potentially even life. Finally, consider the impact of these altered star formation processes on the structure of galaxies. If the rate and style of star formation shift dramatically, entire galaxies could change shape or evolve differently over time, leading to new types of galactic structures that we may have never observed before. The balance of dark matter, gas, and stellar mass would all contribute to a dynamic interplay, redefining how we understand the evolution of galaxies. When we alter the way stars form, we not only create unusual celestial bodies, but also reimagine the very fabric of our universe. Each of these phenomena invites us to expand our understanding of cosmic processes and the intricate dance of matter in space. The formation of galaxies is a complex dance between two major components: baryonic matter, which is the ordinary matter that makes up stars, planets, and living beings, and dark matter, which is a mysterious substance that does not emit light and is detectable only through its gravitational effects. As galaxies were forming, fluctuations in temperature played a crucial role in shaping the relationship between these two types of matter. In the very early universe, shortly after the Big Bang, everything was extremely hot, and matter was in a gas-like state. As the universe expanded and cooled down, baryonic matter began to clump together due to gravity. However, the presence of dark matter was pivotal in this process. Dark matter forms an invisible scaffolding throughout the universe, creating a web-like structure that prevents ordinary matter from drifting away. When the temperature decreased, baryonic matter could lose energy, allowing it to collapse into denser regions where stars and galaxies could eventually form. Dark matter, having gravitational effects, helped pull baryonic matter toward these regions. The balance between the two was influenced by how efficiently baryonic matter could cool down and clump together. If the temperature had shifted to favor darker regions of the universe, it would have allowed darker matter clumps to grow larger and dictate where galaxies formed. Conversely, if baryonic matter cooled too quickly, it might not have effectively interacted with dark matter, leading to less structure and fewer galaxies. This balance is essential because it affects how galaxies are distributed across space. The interplay between the cooling of baryonic matter and the constant presence of dark matter continues to inform our understanding of galaxy formation today, revealing how the universe is so intricately woven together by both visible and invisible forces. In a universe that began with higher temperatures, the formation of planets and their chemical compositions would be quite different from what we observe today. Initially, a hotter environment would mean that elements and compounds would exist in different states compared to our current universe. For instance, gases that are currently found as solids or liquids could remain in a vapor state, affecting how these elements eventually come together. As planets formed from dust and gas in this hot universe, the process of aggregation might prioritize lighter elements. These lighter elements might be more prevalent due to their greater volatility in extremely heat-rich conditions. This could lead to a greater abundance of gaseous plants and less rocky, solid ones than we see now. Moreover, when conditions finally cool, the types of compounds that could condense would also differ, favoring those that are stable at higher temperatures, like different forms of carbon or unique minerals. The distribution of heavy elements, often formed in stellar explosions, could also shift dramatically. If the hotter conditions led to more energetic stellar events, these processes might fuse elements differently, potentially creating a more diverse array of heavy elements in the swirling nebulae that would eventually form new planets. Moreover, the increased energy in such a universe could influence the chemical reactions that take place. For example, high-energy environments could lead to the formation of complex molecules far faster than in a colder universe, potentially fostering the creation of prebiotic chemistry that could differ significantly from that found on Earth. Overall, in a hotter starting universe, we would likely see a major shift in the types of planets that formed, their compositions, and the kinds of chemical processes that ruled their development. This could lead to a rich tapestry of celestial bodies with unique properties and possibly life forms that are unlike anything we know today. In the vast and extreme conditions of outer space, particularly in places like neutron stars or during supernova explosions, the environment can be so intense that it fosters the creation of new exotic elements. Under normal Earth-like conditions, we have a specific understanding of elements based on atomic structures and known reactions. However, in these extreme settings, the laws of physics operate differently, leading to fascinating possibilities. For instance, within neutron stars, gravity is incredibly strong, causing protons and electrons to combine and form neutrons. This results in dense matter composed almost entirely of neutrons. Scientists speculate that under these conditions, matter could exist in states we hardly recognize, like strange quark matter, which is formed from elementary particles called quarks that drift from their usual arrangements. These exotic forms of matter could demonstrate entirely new properties, such as being incredibly dense and stable, yet enormously energetic. Additionally, if we consider the conditions during the early moments of the universe, right after the Big Bang, temperatures were so high that simple hydrogen and helium atoms could fuse into heavier elements. This process could lead to the creation of elements that do not exist today on Earth, combining in unusual ways and possibly leading to materials with extraordinary strength or unusual electrical properties. Exotic elements may not behave like typical elements due to their unique interactions at the subatomic level. For example, they might conduct electricity better than known metals or display unusual magnetic properties. The mere presence of quarks in unusual arrangements could imply that these elements might form stable structures under conditions that would normally lead to instability in more familiar materials. The exploration of these exotic elements is not only a matter of scientific curiosity, but also holds potential applications in advanced technologies, if we can understand how to manipulate them or create them in a laboratory setting. The universe continues to surprise us, presenting opportunities to discover new forms of matter that expand our understanding of physics and the building blocks of everything around us. The chemical changes happening in various environments throughout the universe have significant implications for the emergence of life. To start, life as we know it is based on specific chemical reactions, particularly involving carbon, hydrogen, oxygen, and nitrogen. These elements combine to form essential molecules like amino acids and nucleic acids, the building blocks of proteins and genetic material. In different celestial environments, chemical reactions can lead to a variety of compounds, some of which could provide the necessary ingredients for life. For instance, in the icy moons of gas giants or in the subsurface oceans of exoplanets, we find conditions that can lead to the formation of complex organic molecules. Such environments might not have the familiar warmth of a star, but could still allow for energetic interactions, possibly fostering the emergence of life's precursors. Additionally, the discovery of extremophiles, organisms that thrive in extreme conditions on Earth, suggests that life may not need conditions similar to our planet. This expands the potential for life to exist in diverse environments, such as the high-pressure depths of gas giants or the acidic surfaces of other planetary bodies. The presence of liquid water, a solvent crucial for chemical reactions, alongside a range of temperatures and pressures, opens up pathways for life to evolve in ways we have not yet imagined. Moreover, the search for biosignatures, chemical signs of life, on distant planets becomes essential. The presence of specific gases in an atmosphere, such as oxygen or methane, can indicate ongoing biological processes, suggesting that life might be successful in those far-off worlds. The impressive array of chemical changes occurring in various cosmic settings raises the possibility that life could emerge independently, guided by different chemical pathways and conditions. This ongoing exploration not only challenges our understanding of life's nature, but also invigorates the quest to discover whether we are alone in the universe. Life forms in the universe, if they exist, would likely face a variety of radically different environmental conditions compared to those on Earth. Every planet or moon has its own unique set of features, including temperature extremes, atmospheric composition, gravity, and radiation levels. Let's consider what that means for potential life forms. First, take temperature. On some celestial bodies, the heat could be scorching, while others might be frozen. Organisms on a hot planet might develop ways to regulate their internal temperatures, similar to how some Earth creatures avoid overheating. Those in extremely cold environments might evolve thick layers of insulation or even anti-freeze-like substances in their bodies, allowing them to thrive in icy conditions. Atmospheric pressure plays a crucial role too. On a world with a denser atmosphere, creatures might develop shorter, sturdier bodies to navigate through the thick air. Conversely, if a planet has very low pressure, life could take on a more balloon-like structure to retain necessary gases. These adaptations would be essential for survival. Gravity is another important factor. Higher gravity could lead to life forms that are squat and strong, as they would need sturdy bodies to support themselves. In contrast, organisms on a lower gravity world might grow taller or have more delicate structures since they are not weighed down as much. Radiation levels also impact potential life forms. On planets with thin atmospheres or no protective magnetic fields, life could evolve protective shells or biochemical processes that allow them to cope with or block harmful radiation. Additionally, the nutrients available would shape how life thrives. For instance, a world rich in sulfur might support life that uses sulfur-based chemistry instead of the carbon-based processes we're familiar with. This could lead to entirely different biological systems operating under fundamentally different rules from those on Earth. In conclusion, if life were to emerge elsewhere in the universe, it would need to adapt to each planet's specific environmental pressures and conditions. These adaptations could result in life forms that are vastly different from what we encounter on our own planet, showcasing the incredible diversity that the cosmos has to offer. The constellations and star patterns we observe in the night sky are shaped by the vast distances between stars and our unique position in the universe. If the initial temperature of the universe had been different right after the Big Bang, the formation and distribution of stars, and thus the constellations we see, would likely be altered significantly. Temperature affects how matter behaves. In a hotter universe, atomic particles would have more kinetic energy and would move faster. This means that gas clouds, which later collapse to form stars, would also behave differently. They might disperse too quickly to form stable stars, resulting in fewer stars overall. In contrast, if the universe had been cooler, gas could clump together more easily, possibly leading to an abundance of stars. Moreover, the distribution of elements in the universe is influenced by temperature. A hotter early universe would favor the formation of lighter elements, while a cooler one might allow for more complex structures to form. This would create variations in the types of stars that exist. Certain stars produce more heat and light, shaping constellations in distinctive ways. The patterns we associate with constellations are not permanent. They change as stars move. If the initial conditions had altered the types and numbers of stars, our perception of the celestial canvas would be quite different, leading to the emergence of new constellations and patterns that might have little in common with the ones we currently recognize. So, if the universe had started out at a different temperature, the tapestry of stars we observe today would likely have been woven from different threads altogether, creating a sky that offers new stories and meanings compared to our current view. Cosmic structures, such as filaments and walls, are the vast networks that shape our universe. They act as the framework where galaxies are situated, forming a web that stretches across the cosmos. These structures emerge from the gravitational pull of dark matter, which is like an invisible glue holding everything together. As the universe expands, these filaments and walls are not static. They can change in surprising ways. As the universe evolves, interactions among galaxies can lead to new dynamics. Imagine the filaments as the highways of the cosmos. When galaxies move and collide, they create ripples in this structure, much like how traffic on a busy road can cause jams or divert other vehicles. These interactions can influence the flow of galaxies, leading to new formations or even the collapse of existing structures. On larger scales, the expansion of the universe itself plays a crucial role. As everything stretches outward, the space between these cosmic threads increases. This means that over time, the properties of the filaments and walls could also change. They might grow thinner or denser depending on how matter is distributed and how it responds to this continuous expansion. Moreover, theories suggest that dark energy, another mysterious force driving the universe's expansion, could also reshape these cosmic structures. If dark energy fluctuates or behaves differently over time, it might cause unexpected changes in how filaments and walls form or evolve. The dance of galaxies within these cosmic frameworks will likely lead to an ever-changing landscape, reflecting the dynamic nature of the universe itself. As we explore further, each observation can reveal new layers of complexity and wonder in the vast web of our cosmos. Black holes are fascinating celestial objects that evolve in intriguing ways over time. As stars exhaust their nuclear fuel, they can collapse under their own gravity to form black holes. Initially, black holes can grow by accumulating material from their surroundings. This material spirals into the black hole, forming a disk which heats up and emits powerful radiation. This growth can lead to black holes becoming quite massive. Over time, a black hole's mass affects its future evolution. Smaller black holes can lose mass through a process called Hawking radiation, where particles are emitted from just outside their event horizons, the boundaries beyond which nothing can escape. This gradual loss means smaller black holes may eventually evaporate entirely, potentially leaving behind no trace. When it comes to the singularity at the center of a black hole, this is where current physics struggles. A singularity is a point where the gravitational forces are thought to be infinitely strong, leading to a breakdown of our understanding of space and time. However, scientists now contemplate various theories about how singularities might evolve. Some propose that during times when a black hole merges with another, the singularities might combine, altering their nature. Others speculate that the development of more complex physics might reveal different structures within singularities, creating not just a point of infinite density, but possibly something more intricate. This could change our perception of how information behaves in black holes, which is particularly significant in the study of quantum mechanics and relativity. In the long run, the evolution of black holes could challenge our understanding of the universe itself, merging concepts of general relativity with future insights from quantum physics. As researchers continue to study these cosmic giants, each discovery adds layers to the profound mysteries of black holes and their singularities, constantly reshaping our knowledge about the cosmos. As the universe heats up, significant changes may occur in how quantum mechanics and relativity interact and operate. In a cooler universe, particles are less energetic and tend to behave according to rules that many of us are familiar with. However, in a hotter universe, especially during the early moments after the Big Bang, things become quite different and intriguing. Quantum mechanics describes the behavior of particles at very small scales, where they can exist in multiple states at once and exhibit properties that seem strange compared to everyday experiences. Under high temperatures, particles gain energy and can move faster and collide with more intensity. This energetic environment results in particles consistently interacting, which can lead to new states of matter, such as plasma, a hot soup of free electrons and atomic nuclei. This shift away from stable, low-energy particles suggests that different rules can come into play. On the other hand, relativity deals with how objects behave at large scales and high speeds, particularly in the presence of strong gravitational fields. When we combine the effects of increased temperature with gravity, the fabric of space-time may warp differently. For example, extreme heat could lead to scenarios where classical limits of gravity don't hold. Instead, gravitational forces could impact particle interactions at a fundamental level. Moreover, in a hotter universe, the relationship between energy and mass, as described by relativity, becomes paramount. As temperature rises, the energy of particles increases, which means their effective mass can change. This interplay can lead to different conditions for cosmic structures to form, possibly altering the dynamics of galaxies and black holes. Ultimately, the phase transitions occurring at heightened temperatures may reveal new interactions not previously observable. These shifts challenge our understanding and push the boundaries of both quantum mechanics and relativity, potentially leading to the development of new theories that better unite these fundamental aspects of physics in a rapidly changing universe. As we explore these extremes, we inch closer to unraveling the mysteries of how our universe operates at its most fundamental levels. In the vastness of the cosmos, conditions can be so extreme and different from what we experience on Earth that they might give rise to unique quantum states or even entirely new types of particles. In simpler terms, think of the universe as a massive laboratory, with regions that can be so high in temperature, pressure, or density that they challenge our current understanding of physics. For example, inside neutron stars, which are incredibly dense remnants of burned-out stars, the matter behaves differently. The density is so high that protons and electrons collapse into neutrons, creating a state of matter known as neutronium. This state is not something we encounter in our everyday lives, highlighting the potential for exotic forms of matter under extreme conditions. Additionally, in the hypothetical environments of black holes or during the very early moments of the universe, the laws of physics as we know them may not apply uniformly. Some scientists speculate that new particles could form, possibly leading to forms of matter and energy that are completely foreign to our current understanding. Moreover, in the context of quantum mechanics, particles can exist in unique states that are difficult to fathom. For example, in a process called quantum entanglement, particles can become linked in such a way that the state of one instantly influences the state of another, no matter how far apart they are. This kind of behavior might occur in different ways in environments beyond our reach. So, while we can only imagine what unique quantum states or particles might exist far from our Earth, it's clear that the universe holds the potential for phenomena that challenge our deepest understandings of matter and the laws governing it. Exploring these mysteries could open new avenues in physics, driving our quest for knowledge even further. In the early moments of the universe, just after the Big Bang, temperatures soared to extreme heights. In such a heated environment, the laws of physics operated differently than they do today. To understand how a slight increase in temperature could affect these laws, we should think about the fundamental forces that govern our universe. Under intense heat, particles move with extreme energy, allowing them to overcome forces that usually keep them bound together. Imagine a crowded dance floor where everyone is tightly packed. If the music volume suddenly increases, people start moving wildly, unable to maintain their formation. This is akin to how particles behave at high temperatures, leading to conditions that allow new interactions and formations. One significant result of heightened temperatures is the potential for different states of matter. Typically, we know solid, liquid, gas, and plasma. In a hotter universe, exotic states such as quark-gluon plasma, essentially a soup of fundamental particles, could emerge, altering how matter interacts. As a result, the fundamental forces, gravity, electromagnetism, and the strong and weak nuclear forces may exhibit different strengths or even new behaviors. Furthermore, theoretical physics suggests that under certain conditions, physical constants, which are the underlying rules guiding forces and interactions, can change. If temperature variations could push these constants out of their usual ranges, the dynamics of everything from star formation to galaxy collisions would be drastically altered. If we consider a universe starting with only a delicate increase in temperature, it's plausible that we could witness a slow transition into these different conditions. This might foster the formation of diverse structures or even lead to entirely new types of celestial bodies. An initially slight temperature boost could be the catalyst for redefining the very nature of reality, influencing both the formation and evolution of the universe in ways we have yet to fully grasp. In an alternative cosmic scenario, The formation and geological history of planets could diverge significantly from what we observe in our own universe. Normally, planets form within a star's disk of gas and dust, gradually coming together as particles collide and clump together over vast stretches of time. The makeup of the original material, along with varying conditions like temperature and pressure, creates the building blocks for unique planetary characteristics. In a different cosmic setting, imagine the influence of varied types of stars, or even the absence of certain elements that are crucial for our planets. For instance, if stars formed in different arrangements or at irregular intervals, the gravitational forces acting upon the surrounding material would also change. This could lead to fewer planets forming, or perhaps larger planets consolidating material more quickly, altering their size and density dramatically compared to those in our universe. Moreover, geological processes such as volcanic activity, tectonic movement, and erosion would also differ in this alternative scenario. A planet that forms closer to a hotter star might experience fierce volcanic activity due to the intense heat, creating a landscape dominated by molten rock, while a planet forming in a cooler region may remain frozen for a longer duration, possibly developing icy surfaces with little geological change over time. Additionally, the abundance of gases and liquids, which are essential for weather systems and erosion, would create vastly different atmospheres. For instance, if a planet lacked a significant atmosphere, it could lead to a surface that remains unchanged for millions of years, while another planet with a rich atmosphere might be sculpted continuously by wind and water. In this scenario, the emergence of life could be impacted too, driven by the diverse planetary conditions. Some worlds may host thriving ecosystems due to ideal environmental factors, while others may remain lifeless or could entirely evolve in unique ways based on their distinctive geological histories. Thus, the formation and geological history of planets in an alternative cosmic scenario could lead to an astonishing variety of worlds, each shaped not just by their formative processes, but by the intricacies of their surroundings and the laws of physics that govern their existence. Planetary atmospheres can indeed develop unique characteristics shaped significantly by their initial heat conditions. When a planet forms, it gathers materials from the surrounding space, and the energy from this process generates heat. This initial heat can affect how gases accumulate and interact in the planet's atmosphere. For a planet that forms closer to its star, like Mercury in our solar system, the intense heat can lead to a thin atmosphere made up of lighter elements that can escape into space. In contrast, a planet farther from its star, such as Neptune, may retain gases like hydrogen and helium, leading to a thick atmosphere. The amount of heat also determines how volatile compounds behave. Warmer conditions may favor the presence of gaseous forms of substances, while cooler conditions can lead to liquids or even solids being more stable. Another factor is how this initial heat influences geological activity. A hotter planet might be more geologically active, releasing gases like carbon dioxide or water vapor through volcanic eruptions. These gases can contribute to the long-term composition of an atmosphere, sometimes leading to the development of greenhouse conditions that warm the planet even further. Thus, the initial heat increment not only influences the immediate formation of an atmosphere, but also sets the stage for ongoing interactions and changes that can give rise to the distinct characteristics we observe in different planetary atmospheres today. Each combination of initial conditions and subsequent geological activity leads to a fascinating diversity in how atmospheres can evolve. Temperature plays a crucial role in shaping the climates of planets. When we consider a shift in temperature, it can lead to a variety of effects that influence climate patterns across different worlds. Imagine the surface of a planet as a canvas where temperature dictates how paint can spread. If a planet experiences an increase in temperature, it could mean more energy in the atmosphere. This can result in stronger winds, altered precipitation levels, and changes in seasonal cycles. Warmer temperatures often lead to more water vapor in the air, and this can create a more humid environment, playing a significant role in cloud formation and storms. In contrast, a decrease in temperature could lead to drier conditions in some regions, resulting in droughts or even the formation of ice and snow where water would otherwise flow freely. These temperature shifts also affect the types of ecosystems that could thrive on a planet. For instance, warmer climates might support lush forests and diverse wildlife, while cooler conditions could lead to tundra or desert landscapes, each with its unique flora and fauna. Moreover, shifts in temperature can influence where life could exist, fostering scenarios that could support flying creatures in warm areas or resilient plants in colder zones. The interaction of temperature with other factors, like atmospheric composition and distance from a sun-like star, adds further complexity. Every planet's unique conditions can lead to unimaginable climates, from the scorching winds of a desert world to the ice-covered expanses of an Arctic planet, creating the potential for extraordinary diversity in planetary environments. Hence, understanding temperature shifts is key to predicting how planets develop their climates and what kinds of life, if any, might emerge in those varying settings. The concept of a hotter initial universe expands our understanding of the cosmos and raises intriguing questions about multiverse theories. Initially, the universe is thought to have been incredibly dense and hot, filled with a uniform energy that eventually cooled and led to the formation of galaxies, stars, and planets. This hot beginning hints at a dynamic process that could suggest multiple parallel universes existing alongside our own. The idea of the multiverse proposes that there are many different universes, each perhaps with its own unique properties and physical laws. If the early universe were hotter, it could imply that the conditions necessary for different types of universes to form were more common. Higher temperatures may lead to a greater variety of energy states and interactions, allowing various regions of space to evolve differently, potentially giving rise to distinct universes with their own set of rules. In this scenario, the diversity of universes could stem from tiny variations in the initial conditions. Each universe might be shaped by slightly different forces or fundamental particles. A hotter universe might also have influenced the ways that cosmic inflation occurred, where the universe expanded rapidly after the Big Bang. Variations in inflationary processes could lead to infinitely different outcomes in different regions, producing a vast multiverse landscape. This perspective supports alternative interpretations in which entire universes are born from our universe's early state, suggesting a complex tapestry of realities coexisting. Whether or not our universe is an outlier with unique traits may depend on the luck of the draw during those fiery earliest moments. Thus, a hotter beginning not only gives us a deeper insight into how our universe came to be, but also opens the door to understanding the potential existence of countless other universes, each creating their own unique stories in the grand narrative of existence. In multiverse theories, the idea is that our universe is just one of many, each existing with its own set of physical laws and properties. Now consider what happens when temperatures rise significantly. This increase can have far-reaching effects on how new universes might form. As temperatures climb, it can lead to greater energy levels within a given region of space. This abundance of energy can create conditions suitable for the birth of new universes. Think of it like a cosmic oven. Just as increased heat can cause dough to rise and expand, heightened temperatures in the fabric of space could lead to the expansion of singularities. In these singularities, where density and energy are incredibly concentrated, the conditions might be ripe for a new universe to emerge. Depending on the multiverse model, these new universes could potentially spring forth from existing ones, like bubbles in boiling water, each with its own unique characteristics. The influence of temperature may also alter the fundamental forces that govern these new universes, affecting their development and evolution. Moreover, if high temperatures persist, it might trigger processes similar to what we theorize happened at the beginning of our own universe: rapid expansion, cooling, and the formation of matter from energy. However, the nature and stability of new universes can vary widely based on their specific starting conditions. Some might evolve successfully into stable entities, while others could collapse back into chaos. Understanding how temperature impacts the creation of new universes is crucial in these theoretical frameworks. It opens doors to exploring the very fundamental nature of reality, showcasing how interconnected and dynamic the multiverse can be. Each new universe would not just be a mere copy of its predecessor, but rather a distinct evolution shaped by the unique conditions of its inception. The idea of overlapping or interacting universes comes from the concept of the multiverse, which suggests that there may be many different universes, potentially with different physical laws or realities. If we think about space and time as a fabric that can be stretched and warped, changes in this fabric could, in theory, create openings or connections between distinct universes. Imagine that each universe is like a bubble floating in a vast ocean. Normally, these bubbles drift apart, each following its own path. However, if the fabric of spacetime were to shift due to significant cosmic events, like a massive explosion from a star, or perhaps even the effects of a black hole, these bubbles could come close enough to touch or interact. Such interactions might allow energy or information to cross over between universes, achieving what we call overlap. Though intriguing, this concept remains firmly in the realm of speculation and theoretical physics. Scientists continue to explore these ideas using mathematical models and computer simulations, but no tangible evidence currently suggests that overlap or interaction between different universes actually occurs. The mysteries of the multiverse bring forth countless questions, pushing the boundaries of our understanding and imagination about the cosmos. Dark matter plays a significant role in the structure and behavior of the universe, but it behaves differently than ordinary matter. Imagine that dark matter is like a hidden scaffolding, providing support for galaxies and clusters of galaxies, but it does not interact with light, making it invisible to our eyes. The initial temperature of the universe, shortly after the Big Bang, influenced how this dark matter interacted with other components of the cosmos. When we talk about an initial temperature difference, it's like setting the scene for how everything will unfold. If the early universe was hotter, it would mean that particles were moving faster and were more energetic. This higher temperature could create more turbulence in the formation of structures like galaxies. As the universe cooled, regions of higher density where dark matter began to gather would eventually lead to gravitational wells, pulling in ordinary matter and forming the galaxies we see today. On the other hand, if the initial temperature had been lower, the opposite effects would occur. The speed of particles would be reduced, leading to a slower rate of structure formation. This could mean that dark matter influences galaxies differently, perhaps forming less cohesive clusters or affecting the distribution of visible matter over longer periods. In simpler terms, the temperature difference shapes the way dark matter interacts and affects the evolution of the universe. As a result, the properties of dark matter could change in subtle ways based on that initial temperature. For example, it might affect how well dark matter clumps together or how it interacts with regular matter. Over billions of years, these differences could lead to varying galaxy formations, cluster distributions, and overall cosmic structures. Understanding these initial conditions allows researchers to piece together the early moments of the universe and their lasting impacts. In a slightly hotter universe, the behavior of dark energy could shift notably, raising intriguing speculations about cosmic expansion. Dark energy drives the acceleration of this expansion, acting like a mysterious force that pushes galaxies apart. If temperatures across the universe increased slightly, it might alter the balance between the forces at play. One possibility is that higher temperatures could influence the characteristics of matter and energy. In a warmer setting, particles may move faster and interact more energetically, possibly affecting how dark energy behaves. The dynamics of particles under these new conditions could lead to changes in density and distribution of matter throughout the universe, which in turn might alter dark energy's effects on cosmic expansion. Another speculation is related to the role of dark energy in forming structures. In a hotter universe, the energy density changes, which could either enhance or slow down the growth of galaxies and clusters. This might result in a universe where large structures exist differently than we observe today. Perhaps fewer or smaller galaxies could form due to the increased energy impacting gravitational forces. Moreover, the expansion rate of the universe is closely linked to its temperature. An increase in temperature might lead to more energetic phenomena, potentially leading scientists to consider that the rate at which the universe expands could fluctuate. Depending on how dark energy interacts with an energized universe, we might see acceleration become even more pronounced, or possibly find a way to decelerate if the balance shifts unfavorably. Overall, speculating about dark energy in a slightly hotter universe opens the door to numerous theories, each inviting further exploration and examination. These possibilities not only deepen our understanding of dark energy, but also spark curiosity about the fundamental nature of our cosmos and the forces shaping its destiny. As the universe evolves, the conditions within it undergo significant changes, including heating events that can reshape our understanding of dark matter. Currently, Dark matter is a mysterious substance that doesn't emit, absorb, or reflect light, making it hard to detect. It is believed to make up a large portion of the universe's mass. When we talk about heat increases in the cosmos, particularly during events like the collision of galaxy clusters or the intense energy released from supernovae, we step into a realm of possibilities for new forms of dark matter. Increased temperatures can influence the behavior of particles and their interactions. For instance, if the conditions are right, new particle types could theoretically emerge that might not have existed in the cooler early universe. These particles could potentially fall into the category of dark matter. As scientists explore various high-energy phenomena, they keep an open mind for discovering new types of matter that could provide additional clues to dark matter's true nature. Moreover, as the universe continues to cool following various events, these dynamics might reveal aspects of dark matter that were previously hidden. Understanding how heat affects the subatomic world could lead to groundbreaking discoveries. While we cannot predict with certainty whether unknown forms of dark matter will emerge, the interplay between heat and particle interactions opens intriguing avenues for exploration in our quest to comprehend this elusive component of our universe. In an alternate universe, we could witness a range of extraordinary cosmic events occurring more frequently than in our own. One possibility involves supernovae, the spectacular explosions of massive stars that end their life cycles. In this universe, the conditions for star formation might lead to a significantly larger number of these massive stars. Consequently, we would see the spectacular light shows of supernovae erupting more often, creating bright bursts that can outshine entire galaxies for a short time. Another event could be the merging of neutron stars. In our universe, this rare occurrence produces gravitational waves and creates heavy elements like gold. If the density of stars in this alternate universe is higher, these dramatic collisions may happen much more frequently, offering a unique opportunity to study the fundamental forces of nature and the creation of elements from cataclysmic interactions. Additionally, black holes could play a more dynamic role. In this alternate cosmos, the paths of stars and gas clouds might lead to more frequent instances of black hole collisions or the formation of supermassive black holes. When these black holes merge, they not only release energy in the form of gravitational waves, but also reshape the very fabric of space-time itself. There's also the possibility of highly active gamma-ray bursts, which are among the most energetic explosions known. If conditions favor rapid star formation, we might see these brief, intense flashes of gamma rays erupting more regularly, generating an exciting and hazardous environment for nearby stellar systems. Lastly, the formation of exotic structures, like cosmic filaments that connect galaxies, could be more pronounced. In this alternate universe, gravitational forces might create large-scale structures that are more intricate and diverse, affecting how galaxies evolve and interact with one another. These hypothetical cosmic events paint a picture of an alternate universe that teems with dramatic transformations, each revealing the captivating dynamics of celestial mechanics and the mysteries of space. Altered heat levels in the universe can indeed influence the behavior of cosmic events like supernovae and gamma-ray bursts. To understand this, it's essential to consider what supernovae and gamma-ray bursts are at their core. A supernova is the explosive death of a star, often resulting from gravitational collapse when a star exhausts its nuclear fuel. On the other hand, gamma-ray bursts are intense flashes of gamma rays, typically associated with extremely energetic explosions, such as the merger of neutron stars or the collapse of massive stars. When we talk about temperature changes in space, we might be referring to the conditions surrounding these explosions or alterations in the ambient environment where these events occur. For example, if the surrounding gas and dust were to experience increased heat, it could significantly affect how a supernova interacts with its environment after the explosion. This interaction, in turn, could alter the light curves of the supernova, which are the brightness patterns observed over time. In the case of gamma-ray bursts, if there were variations in surrounding heat or pressure, this could impact the jets of material being ejected at nearly the speed of light. These jets are responsible for producing gamma rays, and any changes in their environment could affect their intensity or direction. This means that in a universe with different heat levels, The energy released during these events might manifest in varied ways, potentially altering the spectrum of radiation detected by our instruments. Ultimately, while the fundamental processes driving supernovae and gamma-ray bursts remain unchanged, the environmental conditions altered by heat could lead to different observable phenomena. Understanding these possibilities helps scientists piece together the dynamic nature of the cosmos and how interconnected its processes truly are. Extreme cosmic phenomena, such as quasars and pulsars, might change in nature over vast timescales due to several factors. Quasars, which are incredibly bright objects powered by supermassive black holes at the centers of distant galaxies, can evolve as their black holes consume surrounding matter. Spacefaring species encounter both significant challenges and unique advantages as they navigate altered cosmic conditions. Imagine a spacecraft traveling through an area where cosmic radiation is unusually high. High levels of radiation can be detrimental, as it poses health risks to living beings on board and can damage electronic equipment. To counter this, species might develop advanced shielding technologies or adapt their biology to withstand such environments, ensuring their survival as they venture deeper into space. Additionally, consider the gravitational changes that occur in various cosmic locations. In areas with lower gravity, such as a distant asteroid or a moon, moving around might be easier, allowing these species to perform tasks with less physical effort. However, prolonged exposure can lead to physical degradation, as the absence of stronger gravity can affect muscle and bone density. This prompts the need for innovative solutions, like developing specialized habitats that mimic Earth's conditions to preserve health. Moreover, altered cosmic conditions can create unique planets with rich resources, offering spacefaring species unexpected advantages. For instance, a planet with abundant water ice and a stable atmosphere could serve as an excellent way station for refueling and resupplying during long journeys. This accessibility to resources can alleviate some of the burdens of carrying supplies for entire journeys. On the other hand, navigating through regions of space experiencing extreme phenomena, such as nebulae or wormholes, introduces unpredictability. Filled with dense dust clouds or unstable energy fields, these areas can hinder travel routes and make navigation tricky. Spacefaring species must constantly innovate their technology and improve their navigation techniques to deal with these unpredictable environments. Ultimately, the interplay of obstacles and opportunities in altered cosmic conditions shapes the evolution of spacefaring species. With each hurdle they face, there's a chance for growth and adaptation that could lead to remarkable advancements in technology and biology, enabling them to thrive in the vastness of the universe. In the vast expanse of our universe, the limitations we face in propulsion and energy sources are defined by the laws of physics that govern everything around us. However, if we consider hypothetical conditions, such as those found in alternate realities or far future scenarios, we open the door to creative possibilities. Imagine a universe where the fundamental rules are slightly different, one where gravity is weaker or stronger, or where particles behave in unexpected ways. In such environments, new forms of propulsion could emerge. For instance, if gravity were weaker, it might be easier to harness energy from celestial bodies by creating advanced systems that float or glide, rather than needing to expend large amounts of energy to overcome a strong gravitational pull. Another fascinating possibility involves taking advantage of exotic materials not found in our existing universe. If a new form of matter could exist that has unique properties, humans might develop engines that utilize this material to create thrust in ways we can't currently envision. Picture a propulsion system that taps into the interactions of these exotic particles, generating energy with efficiency that far exceeds our current technologies, like a sail catching an otherworldly wind. Similarly, if energy sources could be harvested directly from the fabric of space-time or harnessed from cosmic phenomena like black holes, we could see significant advancements. Imagine using the powerful gravitational forces around a black hole to extract energy, a concept that remains theoretical but tantalizes scientists. In short, while the current limitations of propulsion and energy sources are bound by our understanding of physics, alternative scenarios invite the exploration of groundbreaking technologies that could transform travel and energy consumption in unimaginable ways. As we expand our imagination and understanding of different physical conditions, we reveal a universe brimming with potential and possibility. As we look toward exploring the unique universe beyond our own, we must consider how our strategies and technologies might evolve. First, rather than relying on traditional spacecraft designed for mere travel, future explorations may emphasize adaptable vehicles. These vessels could change their shape and function based on the environment, allowing for better efficiency when encountering varying gravitational fields or atmospheric conditions of distant worlds. Next, robotic explorers could take the forefront. Unmanned probes equipped with advanced artificial intelligence would venture into unknown territories, gathering crucial data without putting human lives at risk. These robots would learn on the go, adjusting their missions based on real-time findings. This flexibility would be key as they encounter environments vastly different from what we know. Communications technology will also need to advance. As distances increase, conveying information back to Earth could experience significant delays. Innovations like relay networks using satellites or dedicated communication satellites positioned strategically would ensure that data travels swiftly and reliably. Enhanced algorithms could compress data into smaller packets, making the transmission of information more feasible even over vast separations. Moreover, the idea of using local resources could revolutionize our approach. Instead of sending everything from Earth, astronauts could rely on in-situ resource utilization, making fuel, water, and even shelter directly from materials found on other celestial bodies. This would not only cut down on costs and the need for extensive supplies, but also enhance the sustainability of long-term missions. Lastly, fostering international cooperation will be crucial. As space becomes a shared endeavor, pooling resources and knowledge from different nations could lead to more effective exploration strategies. Joint missions could harness diverse technologies and expertise, bringing us all closer to understanding the mysteries of the universe. Adapting our exploration strategies and technologies is vital for effectively navigating the unique features of the universe. By developing flexible ships, harnessing robotic assistance, enhancing communication methods, utilizing local resources, and embracing global collaboration, humanity can embark on a remarkable journey filled with discovery and adventure. The cosmos is filled with wonders that inspire stories, beliefs, and mythologies. Imagine a reality where stars are born in spectacular ways, or where entire galaxies collide, creating breathtaking cosmic events. For sentient beings observing this altered universe, these phenomena could fuel their understanding of existence and shape their belief systems significantly. If the cosmos were filled with strange new celestial bodies or phenomena, beings might craft stories explaining their origins and significance. For instance, a bright supernova could be seen as a messenger, a symbol of transformation and rebirth. These beings might interpret its sudden brilliance as a sign of hope, creating rituals that honor the memory of a fallen celestial entity. In this context, the creation of new mythologies might stem from the experience of celestial cycles. Imagine a planet where deep, dark nebulae glow with mysterious colors. Its inhabitants might see these clouds as sources of wisdom, leading to belief systems that emphasize learning and introspection. They could celebrate certain times of the year when these nebulae are most visible, aligning their lives with the cosmic rhythms around them. Additionally, encounters with vast black holes might inspire beliefs centered on balance and the unknown. A civilization close to a black hole may view it as a powerful force, representing both creation and destruction. Their mythologies could be rich with tales of beings that traverse its edges, exploring the thin line between life and oblivion, teaching their descendants about courage in facing the unknown. Moreover, if distances between celestial bodies were vastly different, stories could arise about journeys to other realms, inspiring a belief in exploration and discovery. Sentient beings might create legends of heroics and adventures that emphasize bravery and curiosity, encouraging future generations to seek out the mysteries of the universe. Ultimately, an altered cosmos provides a canvas for imagination, where cosmic events transform into rich tapestries of beliefs that impact how sentient beings understand their place in the universe. Each stellar occurrence can ignite the fires of interpretation, leading to a wealth of diverse mythologies that reflect their experiences, observations, and desires. Ancient cosmic events have likely sparked imaginations throughout history, shaping myths and cultural narratives across human civilizations. Imagine the powerful, bright trails of meteors streaking across the night sky. For early societies, such brilliant displays might symbolize the arrival of gods or foretell significant changes. These celestial occurrences were not just spectacles, they were interpreted as messages, guiding people's beliefs and actions. Consider the impact of the bright explosion known as a supernova. This dramatic event, marking the death of a massive star, could be seen as a sign of great transformation, perhaps as a harbinger of new beginnings or the end of an era. Stories woven around such cosmic phenomena could reflect themes of creation and destruction, influencing the spiritual beliefs of entire communities. Furthermore, eclipses, with their temporary darkening of the sun or moon, often incited fear and awe in ancient people. They were sometimes interpreted as battles between celestial beings, leading to stories that explained these rare occurrences through the lens of mythology. Cultures worldwide have charted celestial patterns, forming calendars that dictated agricultural practices and religious festivals, intertwining cosmic events with daily life. This connection between the cosmos and culture illustrates the profound impact that ancient cosmic events may have had on human society. These stories, sometimes born from actual celestial happenings, reinforced societal norms and provided context, meaning, and a shared identity for those who looked up at the stars. In many ways, the universe became a narrative tapestry, rich with symbolism and significance that still resonates today. Constellations and celestial phenomena have always held a special place in human culture, inspiring awe and reverence across different societies. While constellations made up of stars form recognizable patterns in the night sky, celestial phenomena like comets, meteor showers, and eclipses are often more dynamic and fleeting. Their distinct characteristics evoke different emotions and interpretations. Constellations have been a source of guidance and storytelling for centuries. Ancient civilizations leveraged their patterns for navigation or marking seasons. For instance, sailors relied on the North Star to steer their ships, understanding its significance as a stable point in the vast ocean. Many cultures crafted myths and legends around these star formations, using them to explain natural phenomena or impart moral lessons. In many societies, constellations became symbols of strength, courage, or wisdom, connecting the people to the cosmos in a more permanent way. On the other hand, celestial phenomena often inspire more immediate emotional responses. The sight of a comet blazing across the night sky can feel magical, bringing wonder as it appears suddenly and then vanishes just as quickly. Historically, these events have been seen as omens or harbingers of change, viewed with awe or even fear. A solar eclipse, where the moon temporarily obscures the sun, has often evoked feelings of anticipation or reverence due to its rarity and the dramatic shift in light. These differing aspects reflect how humans interact with what they observe in the sky. The enduring nature of constellations lends them a sense of permanence and continuity, making them significant guides throughout generations. Conversely, the unpredictability of celestial events can lead to deep emotional engagement, painting them as powerful moments that punctuate the fabric of time. Thus, while both constellations and celestial phenomena elevate our understanding of the universe, they do so through uniquely profound lenses, one offering stability and the other momentary clarity, each holding its own revered place in human culture. Imagine a universe where conditions were significantly warmer in the early stages of planet formation. This hotter start could lead to different opportunities for the development of life. Warmer environments would mean that molecules essential for life, such as proteins and nucleic acids, could form and interact more readily. As a result, life might emerge sooner and evolve rapidly due to a more conducive habitat. In such a scenario, civilizations that arise may possess technologies and understandings far beyond what humans can currently grasp. Their advancements would depend on the unique conditions of their homeworlds. For instance, if these intelligent species had access to abundant energy sources due to higher ambient temperatures, they might harness energy in ways that seem like magic to us. They could leverage resources more efficiently, resulting in technologies related to energy manipulation, space travel, or even matters of consciousness that elude our current scientific framework. Socially, these civilizations might exhibit various structures influenced by their environments. With an abundance of resources and energy, they could easily focus on community and collective growth rather than competition. Their societies might prioritize sustainability and living in harmony with their surroundings, leading to communal knowledge sharing rather than individual ownership. Alternatively, if their environments were unstable due to extreme heat, their social structures could become highly adaptable, necessitating constant innovation and resilience. Additionally, communication methods could evolve to suit their surroundings better. For instance, if their atmosphere differed from ours, they might use intricate light patterns or sound frequencies to convey information, expanding the concept of language beyond mere words. Their understanding of the universe might also lead to spiritual or philosophical systems that are vastly different from our own, exploring concepts of existence, consciousness, and reality that challenge human understanding. Ultimately, a hotter start could cultivate civilizations that operate under principles and technologies unfamiliar to us, showcasing the vast potential for diversity in life and intelligence throughout the cosmos. Civilizations in space could exploit residual cosmic heat in several fascinating ways. First, it is essential to understand that this heat comes from remnants of the early universe, as well as ongoing processes like the decay of radioactive elements and thermal emissions from celestial bodies. One practical approach to harness this heat involves creating systems that gather and concentrate warmth from these energy sources. Picture a civilization constructing solar panels, but instead of simply capturing sunlight, they design specialized materials to absorb faint thermal radiation that permeates space. These materials could convert low levels of heat into usable energy, powering their technologies in environments where sunlight is insufficient. Additionally, civilizations could develop technologies that mimic geothermal energy harvesting, similar to methods used on Earth. By tapping into the heat of nearby stars or planetary bodies, they could directly convert this thermal energy into electricity. The versatility of thermal systems allows for advancements in heating, cooling, and even propulsion, offering numerous opportunities for intricate applications. Moreover, sustaining a life support system could be enhanced by recycling and conserving heat. For instance, using advanced insulation techniques could store excess heat generated by machinery or living quarter activities. This accumulated heat would then be redirected to warmth during colder periods or when energy is scarce. Innovations might also arise from adapting to extreme environments. For example, in regions of space with substantial residual heat, technologies could thrive on thermoelectric principles, creating efficient energy conversion systems that utilize temperature differences. By integrating these methods, a civilization could create a harmonious balance, harnessing cosmic heat as a sustainable resource that supports their growth, decision-making, and survival in the vastness of space. In this way, the hidden thermal energy of the cosmos could be a vital player in their technological and societal advancement. Inhabiting an altered universe, particularly one that dramatically differs from our own, perhaps with varying physical laws or new celestial phenomena, could reshape cultural and philosophical perspectives in profound ways. Imagine a realm where gravity is weaker or time flows differently. Such changes would not just be scientific curiosities, they would influence how communities are structured, how people live, and how they understand their place in the cosmos. First, consider the social dynamics. In a setting where resources are more abundant due to easier access to energy or materials, values around competition and scarcity could shift. Societies might prioritize collaboration and sustainability rather than conflict and exploitation, leading to new forms of governance and community living. The way cultures share knowledge, stories, and traditions could deepen as groups unite to explore their new surroundings, fostering a stronger sense of identity tied to these shared experiences. On a philosophical level, the nature of existence would likely come under new scrutiny. If physical laws were fundamentally different, beliefs about life, consciousness, and the universe might evolve. Questions that have long puzzled humankind, about our purpose or the nature of reality itself, might take on new dimensions. For instance, if life thrives in variations we cannot even envision, it could challenge beliefs about intelligence or the uniqueness of human experience. Interaction with diverse life forms could lead to profound philosophical discussions about the interconnectedness of all beings and the ethics of coexistence. Moreover, spirituality could expand or transform. New cosmic phenomena might inspire awe and reverence, prompting a resurgence or reinterpretation of spiritual practices. The environment could lead to the emergence of new belief systems, where the universe is viewed not just as a backdrop for human activity, but as a dynamic entity with which we are inextricably linked. Ultimately, inhabiting a dramatically altered universe offers not just the chance for survival, but a canvas for humanity to redefine itself. It would encourage a collective reimagining of culture, philosophy, and identity as individuals seek to understand their new reality and what it means to exist within it. The cosmic temperature plays a critical role in shaping the universe and influencing the formation of energy-rich resources. Imagine the universe as a vast kitchen where different elements and compounds come together under varying conditions. When the temperature of the cosmos changes, it's like adjusting the heat on the stove. It affects how these ingredients mix, react, and ultimately create new substances. In the earliest moments after the Big Bang, the universe was incredibly hot. As it cooled over time, hydrogen and helium atoms formed, which are the building blocks of stars and galaxies. In this cooler environment, stars began to ignite, generating heat and light through nuclear fusion. As these stars live and die, they expel material back into space, enriching the surrounding gas with heavier elements like carbon, oxygen, and iron. These heavier elements are essential for forming planets and can lead to the creation of resources like coal, oil, and natural gas through specific geological processes. If the cosmic temperature shifts significantly, it can alter this entire sequence. For instance, if the universe cooled down too much, star formation might slow or even cease, limiting the production of heavy elements. Conversely, a hotter universe might speed up reactions, potentially leading to rapid star formation, but also creating an environment that could destroy resources before they have the chance to coalesce into planets. Moreover, temperature variations can affect the distribution of resources throughout galaxies. In regions of space where temperatures are higher, stars might form more rapidly, while in cooler areas the same may not occur. The dynamics of gravity and radiation pressure also come into play. Regions with significant amounts of energy might attract more matter and thus become hotspots for resource accumulation, resulting in uneven distribution across the universe. Ultimately, the cosmic temperature not only dictates the patterns of star and planet formation, but it also has far-reaching consequences for where and how energy-rich resources accumulate. Understanding this intricate relationship helps scientists grasp the evolving nature of the universe and the intricate web of energy resources we rely upon. In the earliest moments after the Big Bang, the universe existed in a state that was extremely hot and dense. Under these conditions, energy took on forms that might seem quite strange to us today. One of the most significant forms of energy that emerged was thermal energy, which is the energy due to the temperature of particles moving at incredibly high speeds. This thermal energy led to the creation of fundamental particles like quarks and electrons, which, when combined, eventually formed protons and neutrons. As the universe expanded and cooled, these particles began to combine into atoms, primarily hydrogen and helium, and in this process, a different form of energy appeared, nuclear energy. Inside stars, immense gravitational forces lead to nuclear fusion, where lighter elements join together to form heavier ones. This release of energy is what powers stars, including our Sun. In addition to these well-known forms, there might be more exotic energy sources that are theorized to arise from the conditions during that very early stage. Concepts like dark energy, which is believed to make up a large portion of the universe and drive its accelerated expansion, are still poorly understood, but could have roots tracing back to those hot beginnings. Some scientists also contemplate the possibility of forms of energy that we have yet to discover, such as those stemming from quantum fluctuations. The extreme temperatures of the early universe could have created temporary particles and energies that do not currently have a place in our standard understanding of physics, hinting at a treasure trove of energy forms that might exist in realms we have yet to explore. The quest to uncover these novel forms of energy intertwines with our search for a deeper understanding of the universe's history and its ultimate fate. Each new discovery in energy forms could reshape our understanding of both the cosmos and the laws that govern it. As civilizations develop in the universe, their strategies for acquiring and utilizing resources are likely to evolve in fascinating ways. Initially, a nascent civilization might focus on local resources. Think about how early humans utilized the materials available around them, such as stone or wood. In an extraterrestrial context, the first settlers on a new planet would similarly exploit nearby natural resources like minerals, water, and arable land. However, as these civilizations grow, they are often faced with challenges such as resource depletion, environmental changes, or overpopulation. To adapt, they may develop advanced technologies to extract resources more efficiently. For example, they could use automation or robotics to mine asteroids, maximizing yield while minimizing human labor and risk. This shift mirrors how technological advancements have allowed human societies to move from manual labor to mechanized processes, enhancing productivity. Eventually, civilizations might reach a point where they need to look beyond their home planet or system. This would mark the beginning of interstellar resource utilization, leading to strategies involving resource extraction from other celestial bodies. Imagine spacecraft designed to gather helium from gas giant planets or harvest water from icy moons. Such innovations would expand their resource base dramatically, opening new avenues for energy production or supporting population growth. Moreover, the concept of sustainability could play a crucial role in the evolution of these strategies. As civilizations become aware of their environmental impact, after witnessing the destructive consequences of resource mismanagement, they may adopt circular economy principles. This approach emphasizes reusing materials and minimizing waste, leading to more efficient resource usage across entire ecosystems. In some cases, civilizations might even develop symbiotic relationships with their surroundings, using biotechnology to help cultivate resources naturally, farming alien life forms or genetically engineering plants to thrive in harsh environments. This advances not just their own resource acquisition, but also encourages ecological balance. Ultimately, the evolution of resource acquisition and utilization strategies will be shaped by a civilization's technological prowess, environmental awareness, and the ever-changing challenges they face. As they adapt, these strategies could lead to innovative solutions that maintain prosperity for generations, fostering a sustainable future amidst the stars. Altered cosmic conditions, like those found near massive objects or in extreme environments, can profoundly influence how we perceive and experience time. At the heart of this phenomenon is the concept of gravity. When gravity is strong, as it is near a black hole or a neutron star, the warping of space and time occurs. This means that time can appear to slow down significantly for someone in that intense gravitational field compared to someone far away in a different region of space where gravity has a weaker influence. Imagine standing on a high mountain while a friend remains at sea level. You both have clocks, and as you look down, you notice that your friend's clock ticks at a regular pace, while yours seems to tick more slowly. This difference is not merely symbolic. It stems from gravitational effects that cause time to elapse at different rates based on proximity to massive objects. Additionally, the expansion of the universe affects time as well. As galaxies move away from each other, their light becomes red-shifted, which means that the wavelength stretches and the light shifts towards the red spectrum. This also hints at a change in time perception on a cosmic scale. If we were to look at the distant past of the universe, we would see its evolution in a different timeline from our own. Further, human perception of time itself can vary based on conditions experienced. Under extreme stress or in moments of great beauty and clarity, people often report that time seems to slow down or speed up. This psychological aspect interacts with cosmic conditions, creating a complex tapestry of how we understand and feel time. Overall, whether through the powerful gravity of celestial bodies or the vast scale of cosmic expansion, the perception and flow of time are not fixed but highly variable, influenced by the conditions and forces at play in the universe. The changes occurring in the environment of a planet can profoundly affect the evolutionary processes for species that inhabit it. Imagine a world where temperatures soar or plummet unexpectedly. Such shifts would impose stress on living organisms, influencing their survival and reproduction. Species that can adapt to new conditions, like altered temperatures or availability of resources, may thrive, while others that cannot keep pace often face extinction. This selective pressure leads to what's known as natural selection, where advantageous traits become more common in a population over generations. For instance, if a planet experiences severe droughts, plants that can store water more effectively may dominate, while those that cannot may diminish. This shift eventually alters the entire ecosystem, reflecting significant changes in biodiversity. Furthermore, when species are forced to adapt to new environments, they may develop new characteristics. This process is known as adaptation. For example, if a species must start to eat different foods due to availability, it might evolve physical changes in its mouth or digestive system over time. Planetary changes can also lead to speciation, which happens when populations of a species become so different that they can no longer interbreed. If changes create barriers, like oceans forming or mountains rising, groups may become isolated and evolve separately, leading to distinct species over time. Overall, the interplay of environmental changes, survival challenges, and adaptation creates a dynamic tapestry of life. These evolutionary processes are not just about individual survival. They contribute to the rich diversity of life forms found on a planet, showcasing the resilience and adaptability of species in the face of change. As environments continue to shift, understanding these impacts becomes crucial, not just for the species involved, but also for the interconnected ecosystems they inhabit. Time dilation is an intriguing aspect of how we perceive time in relation to gravity and speed. In our current understanding, time dilates or slows down in the presence of strong gravitational fields and for objects moving at significant speeds. Now, if we consider a hotter universe, the key factors at play are temperature and the behavior of particles within that environment. In a hotter universe, particles would possess more energy and move faster. This increase in speed could lead to noticeable time dilation effects for those rapidly moving particles compared to a stationary observer. However, it gets a bit more intricate when we look at gravity. In a universe that is expanding and heating up, there might be changes in the distribution and intensity of gravitational forces. For instance, if hot regions tend to be spread out with lower densities, their gravitational influence would be lesser compared to a colder, denser universe. If gravity is weaker in hotter regions, the time dilation effects caused by gravity could lessen. In a hotter universe, time dilation phenomena could vary. Faster-moving particles might experience greater time dilation due to their speed, while weaker gravitational forces might lead to less significant dilation effects overall. Therefore, it becomes a balancing act between increased energy and speed versus the potential reduction of gravitational influence. This interplay between speed, gravity, and temperature creates a fascinating landscape for understanding how time is experienced differently throughout the universe. As the universe continues to expand, it experiences a gradual cooling trend. This shift in temperature has profound implications for the long-term fate and life cycle of the cosmos. To understand this, envision the universe as a giant balloon gradually inflating. As the balloon expands, the air inside it spreads out, leading to lower temperatures over time. Currently, the universe is filled with remnants of heat from the Big Bang, known as cosmic microwave background radiation. As the universe cools, molecular activity slows down and stars begin to burn out. Without the necessary fuel, some stars will transform into white dwarfs, while others might go on to become neutron stars or black holes. Essentially, the vibrant life cycle of stars will gradually diminish, leading to a darker, quieter universe. The temperature decrease will also affect galaxies. They may drift further apart as the expansion accelerates, and interactions between them will become less frequent. Over unimaginable spans of time, galaxies could become isolated islands in an ever-expanding void, where the only thing that keeps them company is the cold cosmic background radiation. As this process continues, the universe might eventually reach a state known as heat death. In this scenario, everything would cool down to a uniform temperature where no significant energy differences exist. Without those differences, the processes that drive the creation of new stars or the dynamism of galaxies would cease. Matter would still exist, but the universe would become a lifeless expanse dominated by evenly spread energy. Ultimately, this temperature shift signifies the transition from a vibrant, star-filled universe to a tranquil, cold one, marking a dramatic evolution in the cosmos. It invites us to ponder our place within this vast timeline and the fate awaiting all celestial bodies in an endlessly expanding universe. The end stages of the universe could indeed vary significantly based on the initial conditions present at its formation. Imagine the universe beginning as a tiny, incredibly hot and dense point. This moment, known as the Big Bang, set the stage for everything that followed, including the formation of galaxies, stars, and ultimately, life as we know it. These initial conditions, how much matter and energy existed at that moment, its distribution, and the rate of its expansion, are crucial. For instance, if the universe had slightly more matter, gravity might pull everything together in a big crunch, where the universe collapses back into that initial point. In contrast, if there had been slightly less matter, the universe could expand forever, leading to a cold and dark end where galaxies drift apart until all stars burn out. There's also the possibility of a balanced scenario, where the expansion slows down to a halt. This would create a stable universe where galaxies and stars maintain their distances, but life would face challenges as stars eventually die. Each of these potential futures hinges on those early moments right after the Big Bang. Furthermore, theoretical concepts like dark energy further complicate the picture. Dark energy is thought to drive the acceleration of the universe's expansion. If dark energy behaves differently than scientists currently understand, it could lead to outcomes that are drastically different from what we foresee today. Thus, the universe's fate is deeply intertwined with its origins. Even the smallest variations in those initial conditions could send it down a dramatically different path, leading to a diverse array of possibilities for how it might ultimately end. Imagine a universe that began its existence just a tiny bit hotter than what we know. From this small difference, the implications could be profound. In our familiar universe, following the Big Bang, the rapid expansion created conditions that allowed atoms to form, leading to stars, galaxies, and the complex structures we observe today. However, if the initial temperature was slightly elevated, the physics governing that early stage changes significantly. With higher temperatures, matter would remain in a more energetic state for longer. The intense heat could delay the formation of the first atoms, and thus, stars might take longer to ignite. This could lead to a universe where stars burn hotter and faster. Imagine a cosmos filled with incredibly bright stars, burning brightly but for a shorter period, ultimately leading to a quicker life cycle of stellar populations. These immense stars would end their lives in explosive supernovae, producing heavy elements at a faster rate. Moreover, the darker side of this hotter universe could manifest through increased rates of fusion and energy output. Many stars might explode without the opportunity for planets to cool down and form life. The stages of evolution in such a universe would be drastically altered. Galaxies might be more densely packed with intense radiation, creating conditions that are less favorable for life as we know it. The intense energy might prevent moons and planets from stabilizing around stars, leading to chaotic orbits and abrupt climatic shifts. As time progresses, this universe could evolve into something starkly different from our own. The greater prevalence of black holes formed from massive stars would lead to an environment where these mysterious entities dominate. Over billions of years, galaxies could collide, creating violent interactions that churn matter into a cosmic soup of energy and radiation. In the very end, we could witness a universe that faces a bitter fate due to its initial heat. Stars would burn out quickly, and as they do, the universe might suffer from a form of heat death, where all usable energy is exhausted, and it becomes a dark, cold expanse, lacking the vibrant structures we see today. This speculative scenario paints a picture of how a minuscule change in temperature at the universe's beginning might ripple through the ages, shaping a chaotic and sterile cosmos where the delicate balance that allows for structure, life, and beauty is entirely undone. The idea of cross-dimensional gateways or anomalies often evokes thoughts of science fiction, but let's consider what a slightly warmer universe might mean. Temperature in the universe is tied to the energy of particles. If our universe were even a little bit hotter, it could influence the behavior of matter and energy in significant ways. When we think about dimensions, we often envision them as different layers of reality that could potentially be accessed. In a hotter universe, particles move faster and interact more violently. This increased energy could lead to conditions that allow for strange phenomena. For instance, when energy levels are elevated, it might result in fluctuations in space-time, which are theorized to be necessary for phenomena like wormholes. However, simply warming the universe might not directly create gateways to other dimensions. It could create more opportunities for unusual interactions and anomalies, but the nature of dimensions themselves is complex and involves aspects of physics that we are still trying to understand. Many theories in physics, such as string theory, suggest that extra dimensions exist alongside ours, but accessing them might require conditions far beyond just a rise in temperature. While a hotter universe may increase the potential for unique and dynamic events, there is no guaranteed increase in cross-dimensional travel. The intricate and delicate balance of forces and structures in the universe plays a crucial role in how dimensions interact. Therefore, while the concept is exciting, it remains a puzzle wrapped in layers of scientific inquiry that we are only beginning to unravel. Imagine civilizations existing on planets orbiting distant stars, with their own unique forms of life and levels of technology. If these beings were able to perceive cosmic phenomena like black holes, wormholes, or even supernova, their interactions would likely depend on their understanding and technology. For instance, if a civilization could harness the energy of a black hole, they might develop methods to capture the immense gravitational forces at work. This could provide a near unlimited power source. However, doing so would require advanced technology to safely navigate the perilous environment surrounding the black hole, as anything venturing too close would be pulled in and lost forever. Wormholes, on the other hand, represent a fascinating possibility for travel. Should a civilization recognize these cosmic shortcuts, the ability to navigate through them could revolutionize their understanding of space travel. They might design sophisticated vehicles capable of entering these phenomena, potentially allowing them to explore the far reaches of the universe in a fraction of the usual time. The challenge would be ensuring that they could safely enter and exit these pathways, avoiding the dangers of collapsing structures and the unknowns of what happens inside. Supernovae also present intriguing scenarios. If a civilization could understand how to harness the blast waves or the elements produced from such explosive events, they might leverage these energies or materials for their development, using them as powerful sources of energy or unique building blocks for new technologies. Yet, interaction with these cosmic events would not be without risks. Beings at any level of advancement would need to be cautious, as the unpredictable nature of the universe can lead to abrupt changes that can threaten their safety. Whether they observe from a distance or attempt to manipulate these forces, their journey would be a dance of curiosity, caution, and ingenuity, always striving to unlock the mysteries held within the cosmic tapestry. To understand cross-dimensional occurrences, we delve into several theoretical frameworks in physics. One of the most famous among them is string theory. This idea suggests that the fundamental components of the universe are not particles, but tiny vibrating strings. These strings can exist in multiple dimensions beyond the three we experience daily. By utilizing these extra dimensions, string theory opens the door to possibilities such as parallel universes and alternate realities, allowing for the notion that different dimensions could interact or overlap. Another significant framework is the concept of quantum mechanics, which deals with the behaviors of tiny particles. In quantum mechanics, particles can exist in multiple states or locations at once until observed. This phenomenon, known as superposition, implies that what we see is only one aspect of a more complex reality. Some theorists propose that this can relate to cross-dimensional experiences, suggesting that particles might be able to access other dimensions without us noticing. Then we have the idea of the multiverse, which builds on concepts from both string theory and quantum mechanics. This framework posits that there may be many universes, each with its own set of physical laws and dimensions. If these universes can somehow interact, it could explain bizarre occurrences that seem to defy our conventional understanding of space and time. Lastly, theories about brains, which are multidimensional objects, provide another layer of exploration. In some advanced concepts, our entire universe could be one of many brains floating in a higher dimensional space. Interactions between these brains could cause events that we might interpret as cross-dimensional occurrences. Together, these theoretical frameworks create a rich tapestry of ideas. They not only stretch our understanding of reality, but also ignite curiosity about what could lie beyond our current perceptions of the universe. Each framework offers unique insights that collectively push the boundaries of science and imagination. As the universe continues to expand, it also grows hotter due to the energy of stars and cosmic events. This change in temperature and the dynamic nature of cosmic structures can have contrasting effects on how different regions of the universe interact with each other. On one hand, a hotter universe may lead to increased cosmic isolation. As galaxies move farther apart due to the expansion, there is less gravitational influence between them. This means that the opportunity for galaxies to merge or interact becomes rarer. In this scenario, with distances stretching and celestial bodies drifting away from each other, the vast emptiness of space could foster isolation among populations of stars, planets, and other cosmic components. Conversely, the rising temperatures, especially in areas with active star formation, can create more energetic regions that may enhance interstellar connectivity. Hotter, denser areas of gas and dust might encourage new stars to form and could lead to interactions where matter is exchanged. This could create avenues for influence and even the transfer of materials across distances, potentially leading to new star systems or influencing the development of life. A hotter universe poses a duality. While it can foster greater isolation by stretching cosmic distances and reducing interactions, it may also fuel energetic processes that connect regions in unexpected ways. The ultimate outcome hinges on numerous factors, including the rate of expansion, the distribution of matter, and how various forces in the universe interplay over time. The future of cosmic connectivity will depend not just on temperature alone, but also on the intricate balance of these ever-evolving cosmic phenomena. As we explore the dynamic nature of space, particularly in the context of expanding or contracting spatial dimensions, communication technologies must evolve to keep pace with these changes. Imagine the fundamental challenge of transmitting information across vastly different environments, where distance and time can behave unpredictably. Firstly, communication technologies might employ advanced signal processing methods to ensure clear transmission, even when the laws of physics shift. By utilizing adaptive algorithms that can adjust the way data is encoded and transmitted, these technologies could maintain clarity, minimizing losses or distortions in transmission due to varying spatial conditions. This is akin to having a flexible language that can adjust its grammar depending on the complexity of the subject at hand. Another key adaptation could involve the development of more resilient networks. In an ever-shifting spatial landscape, networks might need to be decentralized. Instead of relying on fixed infrastructures, communication could be facilitated through a web of interconnected devices that can dynamically reroute signals. Imagine a system where information finds multiple paths to reach its destination, much like how water will find several routes in a changing terrain. Furthermore, we could see the integration of quantum communication methods. By leveraging the properties of particles at the quantum level, such as entanglement, it may be possible to transmit information instantly, no matter the distance. This could revolutionize our ability to send messages across vast expanses, overcoming the limits of traditional communication that depends on signal travel time. Finally, the incorporation of artificial intelligence may enhance communication systems by predicting variations in spatial dynamics. With real-time analysis and learning capabilities, AI could manage data flow and optimize signal pathways. This would allow for faster and more reliable communication, much like having a skilled navigator who can adjust course and strategy based on changing conditions. As space itself evolves, communication technologies will likely become more adaptable, resilient, and efficient, ensuring that the flow of information continues even amidst the unpredictable dance of cosmic dimensions. When civilizations face changes in their ability to communicate or travel to neighboring star systems, their reactions can vary widely based on their current technological state, cultural values, and historical context. Imagine a world where humanity suddenly developed the means to send messages to another star system at incredible speeds, allowing for real-time exchanges. The excitement would likely ignite a surge of curiosity and cooperation among scientists, engineers, and ordinary people, as everyone would want to learn what lies beyond our own planet. This newfound contact could foster a sense of unity, both within that civilization and with any potential extraterrestrial neighbors, encouraging an era of exploration and shared knowledge. Now picture the opposite scenario, where distances become insurmountable or communication breaks down. In this situation, it's easy to imagine despair or isolation setting in. A civilization might turn inward, focusing on its internal issues rather than looking outward. This could lead to the risk of stagnation, as innovative ideas and cultural exchanges that often thrive on external interactions diminish. Alternatively, it might push them to develop new technologies to bridge the gap, demonstrating their adaptability and resilience in times of uncertainty. Additionally, how civilizations interpret these changes can deeply influence their philosophies and beliefs. Enhanced contact opportunities might lead to a greater focus on collaboration and understanding, even prompting shifts in governance that prioritize global or universal considerations. Conversely, diminished interaction could breed xenophobia or a sense of abandonment, possibly making civilizations more aggressive towards one another as they compete for limited resources in a perceived hostile universe. These dynamic responses underscore the complex interplay between technological capabilities, societal values, and the ever-expanding cosmos that surrounds us. In an altered universe, the balance of gravitational forces could display fascinating changes that fundamentally affect how celestial bodies interact. Gravitational force is the attraction between objects with mass, and its strength depends on both the masses involved and the distance between them. Imagine if some of the basic properties that govern gravity were altered. For instance, if the mass of planets or stars were increased or decreased, the gravitational pull they exert would change significantly. Larger masses would attract more objects or pull them closer, while smaller masses would struggle to hold on to their surroundings, leading to fewer celestial bodies orbiting them. Similarly, if the distances between these objects changed, it would dramatically impact gravitational interactions. Objects that are closer would experience a stronger pull, potentially resulting in tighter orbits. On the other hand, if they were spaced further apart, the force would weaken, leaving many bodies in a more chaotic state, drifting away or failing to maintain stable orbits. This reconfiguration of gravitational dynamics could lead to previously unseen configurations of stars, planets, and even galaxies. Some might collide, while others might become isolated. The entire structure of that universe could shift, leading to unique astrophysical phenomena, such as unusual star formations or exotic planetary systems. If the balance of gravitational forces is altered, the cosmos would respond in surprising ways, creating a landscape that challenges our understanding of the universe and its underlying mechanisms. Yes, the initial thermal conditions of celestial bodies can influence their rotational and orbital behaviors. When a planet or moon forms, it coalesces from a spinning cloud of dust and gas. The temperature in this region can affect the properties of the materials that make up these bodies. For example, hotter regions might allow for softer materials, which could flow and redistribute differently compared to those that cool down quickly and harden. If a body forms when it is very hot, it can rotate faster as it loses energy more readily and stabilizes into its final form. On the other hand, if it cools slowly, it might maintain a different distribution of mass, which could influence its rotation rate and axis. Additionally, temperature differences can affect how the mass within a body is distributed, leading to uneven shapes or the creation of internal currents that might influence long-term spin. In terms of orbits, the thermal conditions present during the formation process can also affect the distribution of material in a protoplanetary disk, leading to variations in density. This density can result in gravitational interactions, where some bodies might establish stable orbits, while others could experience significant perturbations. Therefore, the initial thermal conditions play a crucial role in shaping not just how a celestial body spins, but also how it moves through space in relation to other bodies. As we explore the cosmos, we must consider unforeseen gravitational and magnetic phenomena that could reveal themselves. One potential occurrence is the existence of undetected celestial bodies, such as rogue planets, which wander through space without orbiting a star. These objects could exert unexpected gravitational forces on nearby stars or spacecraft, affecting their trajectories and orbits in ways we may not anticipate. Another possibility lies in neutron stars. These remnants of massive stars are incredibly dense, with gravity so strong that it curves space-time around them significantly. If a neutron star were to pass close to our solar system, it might alter the movements of planets and even disrupt the orbits of satellites. Magnetic phenomena can also surprise us. The magnetic fields of some planets and other celestial bodies vary dramatically. For example, if we encounter a planet with a highly unstable magnetic field, it could generate unpredictable magnetic storms. These storms might disrupt communication signals or navigation systems on spacecraft passing nearby, creating challenges for exploration. Moreover, dark matter, an invisible substance that makes up a significant part of the universe, is still largely a mystery. Its gravitational effects can influence the motion of galaxies, and encountering regions with higher concentrations of dark matter could change how we understand gravitational fields, possibly leading to entirely new gravitational phenomena that we have yet to observe. As we delve deeper into the universe, we remain on the lookout for these and other unexpected gravitational and magnetic phenomena, continually pushing our understanding of the cosmos and its many secrets. Each discovery opens new avenues of inquiry, leading to a more profound grasp of the forces that shape our universe. The universe is teeming with mysteries that stretch the limits of our current understanding. Among the most captivating of these phenomena are dark matter and dark energy. While we can observe the effects of these forces on galaxies and the universe's expansion, we have yet to uncover their true nature. Dark matter is believed to make up a significant portion of the universe's mass, influencing how galaxies move and interact. Yet it does not emit light or interact with electromagnetic forces, making it invisible and elusive. In addition to these cosmic shadows, rogue planets present another intriguing mystery. These are planets that wander freely through space, detached from any star. The idea of a planet existing without the warmth of a sun raises many questions. How might life develop under such cold and isolated conditions? What could their atmospheres and surfaces look like? Another phenomenon that challenges our understanding is the concept of cosmic inflation, which suggests the universe underwent a rapid expansion immediately after the Big Bang. While this theory beautifully explains certain observations, the exact details and mechanisms remain a puzzle. What triggered this extraordinary burst of growth? What exactly happened in those earliest moments of the universe? Finally, consider the possibility of life existing beyond our comprehension, perhaps in forms that defy our current definitions of biology. These hypothetical life forms might thrive in extreme conditions, like the dense atmospheres of gas giants or the icy moons of distant planets. Their very existence could redefine our ideas about what life means and where it can flourish. Each of these phenomena compels us to question our place in the cosmos and ignites our curiosity about the unknown. As our tools and techniques advance, we may yet unravel these mysteries, revealing the true complexity and wonder of the universe. The quest to uncover the mysteries of space is a powerful catalyst for exploration and discovery. Driven by our natural curiosity, the urge to explore the unknown fosters innovation and scientific progress. When scientists seek answers about the universe, they embark on journeys that lead to the development of advanced technologies and methodologies. For instance, the desire to understand the origins of the universe has inspired the creation of sophisticated telescopes that can peer into distant galaxies, revealing secrets that were once hidden from us. As researchers study phenomena like dark matter and the behavior of black holes, they not only deepen our understanding of fundamental physics but also uncover new avenues of inquiry. This exploration encourages teams from various fields like physics, engineering, and even art to collaborate, sparking fresh ideas and unique solutions. In many cases, challenges encountered in studying space lead to breakthroughs that can be applied in everyday life, such as advancements in materials, science, and communication technologies. Moreover, the thrill of discovery in space ignites the imagination of people around the world. This collective fascination creates a sense of unity and shared purpose, inspiring future generations of scientists, thinkers, and dreamers. As we grapple with questions about our existence and the limits of the universe, the desire to explore not only solves scientific puzzles, but fundamentally transforms how we understand our place in the cosmos. Each new answer gained fuels even more questions, propelling humanity forward into an era of exploration that knows no boundaries. In the realm of alternate universes, the idea of unknown forces or dimensions opens the door to a fantastic exploration of possibilities. Imagine our familiar universe as just one page in a vast book. where each page represents a different universe with its own set of rules and characteristics. In some of these alternative pages, the fundamental forces that govern our reality might behave entirely differently. For instance, gravity, electromagnetism, or even the strong nuclear force might be altered or entirely absent in these other dimensions. Such changes could lead to wildly different forms of matter and energy, resulting in environments that challenge our understanding of physics. The laws of motion might not apply in the same way, allowing for truly unique phenomena that we cannot yet comprehend. Additionally, the notion of extra dimensions adds another layer of intrigue. Beyond the 3 dimensions we experience, theorists suggest there could be hidden dimensions curled up in ways that we cannot perceive. These extra dimensions could influence the structure and behavior of universes differently, perhaps enabling exotic interactions or the existence of new types of particles. In storytelling terms, incorporating these unknown forces and dimensions could create a narrative landscape where the characters and events are subject to rules that differ dramatically from our own. This could lead to scenarios where journeys through space and time are influenced by phenomena we have yet to discover, enriching the overarching tale with unpredictability and wonder. The very fabric of reality may become more complex, inviting endless questions and thrilling possibilities for exploration. Heat plays a critical role in the preservation and discovery of ancient extraterrestrial artifacts. These artifacts, which could be remnants of past alien civilizations or materials from other worlds, can be affected in a number of ways by changes in temperature. First, increased heat can lead to the deterioration of materials. Many substances, whether they are organic or inorganic, can become fragile or break down when exposed to extreme temperatures over time. This is particularly true for organic materials, such as any possible biological remnants, which may degrade or disintegrate entirely in warmer conditions. Consequently, if ancient extraterrestrial artifacts are buried in environments that experience significant temperature increases, their chance of survival diminishes. On the other hand, heat can also play a role in amplifying geological and atmospheric processes that may unearth these artifacts. For instance, as temperatures rise, ice and permafrost in polar or mountainous regions can melt, potentially revealing hidden structures or materials that were previously covered and preserved. This melting can sometimes expose artifacts that have remained untouched for millennia, opening the door for unprecedented discoveries. Moreover, alterations in heat can change the chemical composition of surrounding environments. This could lead to new ways in which artifacts interact with their surroundings, where factors like oxidation or corrosion become more pronounced. As materials interact differently with heat, researchers might need to adjust their methods for detecting and analyzing artifacts, adapting to find these hidden treasures more effectively. While altered heat can threaten the integrity of extraterrestrial artifacts, it can also act as a catalyst for discovery, revealing ancient cosmic secrets that have long lain in wait beneath the surface. Understanding these dynamics is crucial for both protecting and uncovering the mysteries of the universe. The cosmic history and evolution of our universe provide a rich backdrop for archaeological insights that may seem far removed from our everyday understanding of ancient human cultures. When we think of archaeology, we often picture digs that uncover artifacts and structures from centuries or millennia ago. However, considering the broader context of the universe can influence how we interpret what we find here on Earth. One insight involves the materials from which ancient artifacts were made. Elements like gold, silver, and trace metals are not originally from our planet. They were formed in the hearts of dying stars or during explosive events, such as supernovae, before being scattered throughout space. When archaeologists study artifacts, they are not just examining human creation, but are also tapping into a cosmic narrative, a history that traces back billions of years. This perspective can enhance our understanding of trade routes, technological advancements, and cultural values as they relate to the acquisition and use of these materials. Moreover, cosmic events, such as meteorite impacts, have shaped both the Earth and human history. Archaeological sites can reveal layers of history where ancient peoples interacted with or responded to these events. The discovery of a meteorite might hold information about the technological capabilities of a civilization, revealing how they utilized such celestial gifts for tools or as objects of reverence. Additionally, the evolution of humanity itself is a product of a universe defined by change and adaptation. Just as celestial bodies evolve over time due to gravitational forces and thermal dynamics, human societies have adapted to their environments. Understanding how celestial phenomena like climate conditions influenced ancient settlements can provide insights into migration patterns and cultural shifts. Even studying ancient astronomical knowledge or celestial alignments in structures, like temples or pyramids, gives us a glimpse into how humanity has historically understood and related to the cosmos. These connections between the earthly and the cosmic illustrate that our past is interwoven with the universe's history, enriching our archaeological understanding by placing humanity in a larger cosmic context. In this way, the distinct cosmic history not only serves as a backdrop, but also as an active participant in shaping human culture and civilization, informing us about who we are and how we came to be, all while revealing the deep connections we share with the universe. The discovery of alien ruins would unveil remarkable insights into the adaptability of life in environments vastly different from our own. Imagine a civilization that thrived under extreme temperatures, high radiation levels, or giant atmospheric pressures. Such ruins would provide a glimpse into how these beings built their societies, developed technology, and created art or architecture that reflects their unique survival strategies. For instance, if the ruins were found on a planet with thick clouds blocking sunlight, the inhabitants might have harnessed bioluminescence or advanced technology to illuminate their world. This adaptation showcases creativity in solving everyday challenges. Their structures might reveal insights into their understanding of physics, how they managed weight and stress in their buildings while contending with their planet's gravity. Additionally, analyzing artifacts could provide clues about their social structures. Did they live in cooperative communities, or were they solitary creatures? The artifacts may reflect cultural practices or spiritual beliefs shaped by their surroundings. If they developed tools or technology to utilize local resources, it would indicate a deep connection with their environment, emphasizing how life evolves in response to unique challenges. Ultimately, alien ruins would tell a story of resilience and innovation, highlighting the varied paths life can take under different conditions. They could redefine our understanding of what life is, how it adapts, and what forms it may take in the universe. In the vast expanse of the universe, conflicts can arise from a variety of sources due to differences in resources, energy, and ideologies among emerging civilizations. Imagine two advanced civilizations competing for control over a rare, energy-rich planet. Tensions might escalate as each side harnesses their technological advancements to assert dominance. However, unlike conflicts on Earth, these cosmic confrontations could unfold in vastly different ways. For one, the scale of the cosmos introduces unique strategies. Instead of traditional warfare, civilizations might engage in more sophisticated forms of negotiation or competition that could involve interstellar treaties or resource-sharing agreements. Advanced technologies might allow for peaceful solutions unattainable with earlier methods. Perhaps they develop communication systems that enable real-time dialogue across vast distances, making it easier to reach compromises without resorting to violence. Additionally, the nature of space can shift the dynamics of conflict resolution. Space is filled with countless untapped resources, such as asteroids and comets, which offer alternative paths to growth. If rival civilizations are aware of abundant resources elsewhere, conflict over a single location might be seen as a short-sighted move. They might instead collaborate on exploration missions, pooling their strengths to discover new energy sources, thereby fostering alliances instead of hostilities. Moreover, the vast environments of space encourage a broader perspective. Civilizations could realize that their survival hinges on cooperation in the face of cosmic threats, such as asteroid impacts or rogue celestial phenomena. In this scenario, what begins as a conflict over territory could transform into a united effort against a shared danger, leading to mutual understanding and long-lasting partnerships. Conflict resolution in this universe could therefore not only reflect advanced technological capabilities, but also a deeper comprehension of collective existence. Civilizations might come to understand that thriving together leads to more significant achievements than any individual triumph, paving the way for a future where collaboration prevails over confrontation. As the universe expands and evolves, its characteristics may indeed create conditions that encourage cooperation among advanced civilizations. One of the key aspects to consider is the way these civilizations may perceive resources and challenges. If the universe becomes less stable, or if essential resources become scarcer, different societies might find that collaboration offers a better chance at survival and prosperity. Imagine a scenario where a civilization faces a common threat, such as a cosmic event that could endanger multiple worlds. In such a case, the instinct for self-preservation could lead to an unprecedented level of cooperation. They would recognize that working together increases the odds of overcoming obstacles that might be insurmountable in isolation. Additionally, as knowledge spreads across civilizations, the sharing of scientific discoveries and cultural understandings could encourage mutual respect and admiration. When civilizations realize that they share a common heritage in the stars, a sense of interconnectedness may blossom. This perspective might lead to shared endeavors in space exploration, technological development, or even the preservation of their respective cultures and histories. Moreover, as civilizations advance, their understanding of the universe's complexities may give rise to a more profound sense of empathy. They may become more aware of the fragility of life and the interconnected nature of all existence. This realization could shift priorities from competition to collaboration, fostering alliances that transcend individual ambitions. However, this scenario is not guaranteed. The universe is also filled with unpredictable forces and complexities. Cooperation may depend on various factors, including histories of conflict, differing ideologies, and the ways in which civilizations communicate. Despite these challenges, the evolving nature of the universe could indeed lay the groundwork for extraordinary partnerships among advanced civilizations. Cosmic diplomacy refers to the potential for cooperation among nations, and potentially with extraterrestrial civilizations, regarding the exploration and utilization of space. As humanity becomes more advanced in technology and its presence in space grows, the landscape of diplomacy is likely to evolve significantly. One way this evolution could manifest is through the establishment of international treaties focused on the responsible use of outer space. These agreements would outline standards to prevent conflict over space resources, such as water ice on the Moon, or methods to handle space debris that could threaten satellites. Another important aspect of cosmic diplomacy could be the creation of agencies dedicated to overseeing space activities. These organizations could facilitate collaboration among countries, ensuring that all parties have a say in how shared technologies are used, such as satellite communications or planetary exploration. By working together on common goals, nations could also align their scientific missions, share data, and pool resources to achieve objectives that would be too ambitious for a single country to handle on its own. Moreover, if we discover signs of intelligent life beyond Earth, that could push cosmic diplomacy even further. A need for unified communication and standards would arise, prompting nations to develop frameworks for interaction with extraterrestrial entities. This could lead to a shift in how humanity views itself, fostering a sense of shared identity as Earthlings rather than as citizens of individual countries. This shift could rekindle discussions on global challenges like climate change and resource distribution on Earth, encouraging cooperation in ways never seen before. As technologies advance, the possibilities of space travel and colonization may also create new diplomatic opportunities and challenges. Issues surrounding territorial claims on celestial bodies could require the negotiation of rules that prioritize peaceful exploration over competition. Additionally, creating a legal framework for space mining and settlement will be paramount to ensuring that all of humanity benefits from the resources beyond our planet. Cosmic diplomacy could evolve through international treaties for space use, the establishment of cooperative agencies, and possibly standardized interactions with extraterrestrial life. This evolution would not only address challenges, but also foster a collaborative spirit that could result in unprecedented achievements in science, exploration, and even in addressing challenges we face on Earth. As we explore the wonders of the universe, we also encounter significant ethical dilemmas related to our actions and interventions. First, consider the implications of manipulating natural celestial bodies. If humanity attempts to alter the trajectory of an asteroid to prevent a potential collision with Earth, we face questions of morality and prioritization. The risk of unforeseen consequences is immense. A change that seems beneficial might inadvertently lead to larger disasters for other populations or ecosystems. Understanding the universe also raises ethical issues. For example, the discovery of extraterrestrial life invites moral considerations regarding our responsibility towards these potential beings. If we find life on another planet, should we intervene in its natural evolution? The question amplifies when considering the superior technologies we possess. Do we have the right to impose our will on another form of life, no matter how primitive? Another consideration lies in genetic manipulation, whether on Earth or in space colonies. As we venture into the stars and potentially establish human settlements on other planets, the ability to modify human genetics to better adapt to new environments could lead to a new form of inequality. Those with access to such technologies might elevate themselves above others, creating divisions that challenge the very essence of our shared humanity. Moreover, the act of exploring and potentially colonizing other worlds raises issues about ownership and stewardship. If we claim rights over planets and resources, it implies a hierarchy over the universe. Are we justified in exploiting these resources, especially when we consider the destruction humans have caused on Earth? Here lies a fundamental question. What does it mean to be responsible caretakers of an interstellar ecosystem? As we venture further into understanding and possibly altering our universe, these ethical considerations remind us to tread carefully. Striking a balance between exploration and responsibility is essential, urging us to think about the long-term impacts of our actions, not just for ourselves, but for all forms of existence that may share this vast universe with us. Moral philosophies often grow out of the fundamental challenges that societies face, and when considering cosmic conditions, these challenges can become even more profound. Let's imagine a scenario where humanity finds itself living in an environment that requires cooperation to survive, such as on a distant planet with limited resources. In such a setting, moral philosophies might shift towards values like collaboration, sharing, and collective well-being. People would begin to recognize that individual survival could depend on the community's strength and unity. As cosmic threats, such as asteroids or hostile alien environments, become a reality, the need for a unified approach to risks would likely reshape ethical beliefs. The idea of protecting not just oneself, but the entire group might lead to moral codes that emphasize sacrifice for the common good. A community would promote the idea that caring for one another is paramount, as survival becomes a shared goal. Furthermore, when confronting the vastness of the cosmos, questions about humanity's place in the universe would arise. This might spark philosophical inquiries about existence, purpose, and ethical responsibilities toward other sentient beings. Would humanity feel a duty to respect and protect potential life on other planets? The exploration of such moral duties could lead to the development of philosophies highlighting interconnectedness and stewardship of not only one's planet, but the universe as a whole. The extreme challenges posed by cosmic conditions would likely compel humanity to refine its moral frameworks, evolving them to emphasize survival, cooperation, and respect for life, both familiar and alien. As the understanding of the universe expands, so too would the moral beliefs that guide human behavior in this larger, more complicated cosmic landscape. The idea of advanced civilizations influencing the universe's destiny raises fascinating questions about responsibility and power. Imagine a group of beings with significant knowledge and technological capabilities. With such advancements, they hold the potential to impact everything around them, from their own world to the very fabric of space-time itself. First and foremost, an advanced civilization might have a duty to protect their home environment. This means utilizing their technology to maintain a sustainable balance, ensuring that their planet thrives without exhausting its resources. Such stewardship extends beyond mere survival. It involves nurturing ecosystems, addressing the impacts of climate change, and preserving biodiversity for future generations. Their actions can serve as a model for other civilizations, guiding them towards similar sustainable practices. Moreover, as explorers of the cosmos, these civilizations could be responsible for observing and understanding their surrounding universe. This means studying celestial phenomena like supernovae, black holes, and potentially harmful asteroids. By sharing this knowledge with others, or even developing technologies to mitigate potential cosmic threats, they enhance not only their survival, but also the safety of other planets and species that may inhabit the universe. The ethical considerations grow when one thinks about contact with less advanced civilizations. An advanced civilization must weigh the benefits of sharing technology and knowledge against the risks of cultural disruption or existential threats. They might need to tread carefully, allowing less developed beings to evolve and learn at their own pace instead of imposing their advanced ways upon them. Furthermore, they may play a role in preserving universal diversity, ensuring that the rich tapestry of life and consciousness continues to flourish across the cosmos. This could involve protecting endangered species, fostering the growth of intelligent life forms, or even acting as guardians of ancient knowledge that spans galaxies. Advanced civilizations not only have the power to influence the universe's trajectory, but also the responsibility to consider the ethical implications of their actions. They stand at a crossroads of potential destruction and creation, where each decision can ripple through time and space, shaping the destiny of countless lives and worlds. Such profound responsibilities come with the understanding that they are custodians of the cosmos, tasked with navigating the delicate balance between progress and preservation. As scientists delve deeper into the mysteries of our universe, the understanding of its nature opens the door to revolutionary technologies. One notable possibility lies in the exploitation of quantum mechanics, the science governing particles at their smallest scales. If we could harness the strange properties that allow particles to be in multiple states at once, or to be entangled across vast distances, we could develop incredibly powerful computers. These quantum computers would perform calculations at speeds unfathomable by today's standards, potentially revolutionizing fields from medicine to climate forecasting. Another area with immense potential is the use of advanced materials inspired by cosmic phenomena. Materials that can withstand extreme temperatures, pressures, and radiation could evolve from research into supernovae or the surfaces of distant planets. These materials could transform industries like aerospace, making space travel safer and more efficient. Additionally, understanding these cosmic environments could lead to the creation of lightweight, durable materials for use on Earth, enhancing everything from infrastructure to consumer goods. Energy generation is yet another field that could see groundbreaking advancements. Drawing from cosmic processes such as nuclear fusion observed in stars, scientists aspire to replicate this power source here on Earth. Fusion, which combines light atomic nuclei to release vast amounts of energy, could provide a nearly limitless, clean source of power, transforming our energy landscape. If successful, technology arising from a better understanding of fusion could alter everything from how we power our cities to how we combat climate change. Lastly, the realm of artificial intelligence is poised for growth as our understanding of the universe alters our approach to complex problem solving. By incorporating insights from cosmic phenomena and patterns observed in nature, we might develop AIs that can learn and adapt faster than ever before. These advanced systems could help us manage everything from global resources to space exploration missions, ensuring that we tread carefully and sustainably in our pursuit of knowledge. Each of these technological advancements, inspired by the altered understanding of our universe, is not just about exploiting resources. They represent a shift in how we approach innovation, moving towards solutions that are as much about harmony with the universe as they are about progress. As we continue to explore the cosmos, the potential for groundbreaking technologies could lead to an exciting future, where we find pathways that were once thought to be unimaginable. The cosmic environment is full of extreme conditions, and it can certainly inspire unexpected technological breakthroughs. When we look at space, we see areas filled with high radiation, intense gravity, and extreme temperatures, all of which challenge our current understanding of materials and processes. Engineers and scientists have to think creatively to solve problems in this environment, leading to innovations that can have applications back on Earth. For example, studying the effects of microgravity on biological systems has allowed researchers to discover new ways to develop medicines and even produce food. In the weightlessness of space, scientists can observe how plants grow without the usual forces of gravity influencing their development. This knowledge could change agriculture techniques, improving food security in areas with challenging growing conditions. Moreover, the harsh environment of space pushes the limits of material science. Engineers are constantly looking for new materials that can withstand extreme temperatures or resist radiation. Discoveries made in the quest for better spacecraft can lead to advancements in industries on Earth, such as creating more durable electronics or improving safety in extreme weather conditions. Even the communications technology used in space missions has influenced everyday devices. Techniques developed for transmitting data across the vast distances in space have led to improvements in internet technology, enhancing both speed and reliability. The unique properties of the cosmic environment act as a crucible, fostering innovation while addressing the specific challenges of space exploration. The solutions discovered under these extraordinary circumstances often find their way back to Earth, revolutionizing technology and improving lives in ways we may not have anticipated. In a universe that originated at a higher temperature, fundamental changes in technology might arise due to the differing nature of matter and energy. When the universe begins incredibly hot, atoms barely have time to form, and everything is primarily composed of particles in a chaotic dance. As it cools, atoms could start to bond and build the complexity we see today. However, if the cooling process occurs in a more gentle manner, matter might interact differently, leading to distinct forms of technology and devices. For instance, the abundant energy in a hotter universe could allow for the creation of novel materials with unique properties. Technologies relying on these materials might harness energy in ways we can only imagine, perhaps using heat or light more efficiently than today's solar panels. This could indicate a far greater ability to utilize renewable energy sources, as the materials developed might respond better to such conditions. Moreover, communication technologies might develop differently in a hotter universe. Electromagnetic radiation, which is crucial for our current technologies, behaves differently in environments with extreme energy levels. This could lead to reliance on alternative methods of information transfer, possibly utilizing different frequencies or even unknown particles for communication over vast distances. The tools and machines we create could also reflect the environmental influences of a hotter universe. Space travel, for instance, might advance more quickly in a scenario where energy is plentiful and reactions among particles lead to more powerful propulsion systems. Instead of combustion or electric engines, we might see technologies that manipulate fundamental forces directly, driven by the unique conditions present. In short, technology shaped in a hotter universe would likely involve advanced materials, a focus on harnessing immense energy efficiently, alternative communication methods, and innovative propulsion systems. Each of these developments would fundamentally change how civilizations interact with their environments and each other, leading to entire histories and cultures that unfold under different cosmic circumstances. Consciousness, as we understand it, is deeply influenced by the environment. If we imagine a universe under changed cosmic conditions, the development of consciousness could indeed take a rather different path. For instance, alterations in gravity, radiation levels, or the presence of various planetary types could lead to unique evolutionary pressures. Consider life on a planet where the atmosphere contains a different mix of gases than what we experience on Earth. Organisms would adapt in ways that may result in distinct forms of communication, social structures, and cognitive abilities. The environmental challenges they face might shape their brains and nervous systems, leading to a form of consciousness that is more communal or perhaps more solitary, depending on the survival strategies that prove most effective. In a low-gravity world, for instance, beings might evolve larger brains to handle complex tasks more efficiently, or they could develop entirely different sensory modalities to navigate their space. Alternatively, on a planet with intense radiation, life might evolve heightened protective instincts or adaptability, possibly fostering a consciousness that emphasizes survival over exploration. Furthermore, the nature of the social dynamics in these environments would also play a role. In societies where resources are scarce, empathy and cooperation might be critical traits that evolve, shaping how consciousness develops around social relationships. Ultimately, as we explore these possibilities, we realize that consciousness is not a static trait, but one that could evolve in numerous ways, conditioned by the cosmic landscape. Each unique environment could plant the seeds for different cognitive experiences and ultimately different understandings of existence itself. This means that, in altered cosmic conditions, consciousness may not just evolve differently, but could also lead to forms of intelligence and awareness that are entirely alien to us. In the vast expanse of space, mental and cognitive processes of astronauts may undergo significant adaptation due to the unique environment. Imagine living in a place where the constant pull of gravity does not exist. This absence can alter how our brains process information. For instance, without the familiar weight of gravity, spatial awareness might shift, leading to a different understanding of orientation and movement. This means astronauts could find themselves relying more on visual cues than physical sensations to navigate their surroundings. Moreover, the isolation of space can also weigh heavily on one's mind. Being away from family and friends for extended periods might lead to feelings of loneliness and stress. The brain could adapt by developing new coping strategies or even altering emotional responses to manage the heightened challenges of confinement and distance. This might manifest in stronger teamwork skills, as astronauts learn to rely on each other more than ever, creating a tightly knit community among their ranks. Cognitive processes are also bound to change. The constant exposure to new and complex problem-solving situations, like operating intricate machines or addressing unexpected challenges, may enhance creativity and critical thinking. These mental adaptations are crucial. As one encounters unforeseen circumstances, the ability to innovate and think on one's feet becomes essential for survival and mission success. Additionally, studying these cognitive changes offers a glimpse into how the human mind can be both resilient and adaptable. It shows our capacity to evolve in response to new environments, emphasizing the remarkable features of human psychology. Such observations are not only important for astronauts, but also provide insightful perspectives on human behavior and adaptability that can apply to other challenging situations on Earth as well. In the vast universe, the concept of telepathy and other forms of non-verbal communication sparks imagination about how intelligent beings might connect beyond normal speech. Imagine two creatures, perhaps from different planets, who approach each other without the use of words. Instead, they exchange thoughts or emotions directly, bypassing the barriers that spoken language might create. This form of communication could allow for deeper understanding and empathy, making it easier to share complex ideas or feelings without misunderstandings. Telepathy could serve as a tool for cooperation, enabling groups to work together more effectively. It might allow for instantaneous sharing of information, where one being's knowledge and experiences can flow into another's mind seamlessly. This might be especially valuable in high-stress situations, such as during a conflict or a scientific inquiry, where quick decisions are crucial. Additionally, nonverbal communication could take many forms, such as gestures, body language, or even colors that change on the surface of a being's skin. These methods could convey emotions and intentions in ways that words might not capture, adding layers of meaning and richness to interactions. In environments where sound is muted or distorted, like in the vacuum of space or under the ocean, such communication methods become vital. Moreover, telepathy could have implications for social structures and relationships. Communities might function differently, with relationships built on deep mental connections rather than verbal exchanges. This might lead to societies that are more unified and cooperative, as individuals can engage in mutual understanding on a profound level. Ultimately, telepathy and non-verbal communication highlight a fascinating aspect of how life might exist in the universe, showing that connection and understanding don't always require words, and showcasing the incredible diversity of potential interactions among intelligent beings. In a universe where the origin was significantly hotter, the very fabric of how civilizations evolve could be altered in profound ways. At the birth of such a universe, the intense heat would lead to a rapid formation of matter and energy. This could mean that elements essential for life, like hydrogen and helium, might form differently, possibly resulting in fewer diverse chemical reactions necessary for complex structures. With higher temperatures, planets would be exposed to harsher conditions. For instance, instead of stable environments conducive to life, many planetary bodies could remain molten or have volatile atmospheres. This might lead to fewer opportunities for life to emerge. If life did develop, it would likely be in extreme conditions, possibly resulting in organisms that are vastly different from what we know today. Moreover, in a hotter universe, star formation might surge initially but then destabilize quickly. Stars could burn brightly but not for very long. leading to a more chaotic cycle of creation and destruction. Civilizations that did rise in such a turbulent environment might find themselves facing frequent cataclysms, impacting their growth and technological advancements. The biospheres on planets would also be drastically different. If life forms manage to adapt, they may evolve with unique survival strategies, resulting in ecosystems that are aggressive and resilient. Note that these organisms might develop technologies that reflect their harsh environments, perhaps focusing more on environmental manipulation rather than advancement in societal structures. With a hotter origin, the narrative of civilizations might focus more on resilience and adaptation to extreme conditions. The struggle for survival could become more central, altering the fundamental values and communal structures of any intelligent beings that might emerge. In this alternative universe, adaptability could triumph over prosperity, leading to a history marked by survival against the forces of nature rather than by exploration and expansion. The historical tapestry of our universe is woven with pivotal events that have shaped its very existence. One significant moment occurred shortly after the universe began. Known as the Big Bang, this event marks the birth of space and time about 13.8 billion years ago. It was an explosion that filled the cosmos with energy and established the foundation for everything that would follow. Following the Big Bang, the universe underwent a rapid expansion known as cosmic inflation. During this period, the universe expanded at an astonishing speed. This dramatic growth smoothed out the energy fluctuations that existed, leading to the formation of galaxies and other structures. As the universe continued to evolve, stars began to form from gas clouds. These stars lit up the universe and played a crucial role in the creation of heavier elements through nuclear fusion in their cores. When some stars exhausted their fuel, they went through spectacular supernova explosions, scattering those elements into space. This process laid the groundwork for planets and eventually, life as we know it. Another critical event was the formation of our solar system, a delicate dance of dust and gas that coalesced into the sun and the planets around it. Over billions of years, Earth developed conditions suitable for life. The emergence of life itself, particularly with the advent of photosynthesis, radically changed the atmosphere and allowed oxygen to build up, allowing for complex life to flourish. Moving forward in time, the emergence of intelligence and technology on Earth represents another pivotal phase. The first civilizations formed, and with advancements in science, humanity began to explore its own relationship with the universe. The discovery of gravity, the laws of motion, and the understanding of light have all contributed significantly to our comprehension of the cosmos. Moreover, the exploration of space during the last century has illuminated parts of our universe that were once mysterious. From landing on the moon to sending probes to the outer planets, these missions have greatly expanded our understanding of what lies beyond our home planet. Each of these key events has contributed layers to the rich narrative of the universe. They remind us that the cosmos is dynamic, continually changing and evolving. As we look back at this historical tapestry, we realize that it is not just a story of stars and galaxies, but also one of life, discovery, and an ever-deepening quest for knowledge, driving us to explore and understand more about the universe we inhabit. In the vast expanse of space, where horizons stretch beyond imagination and time behaves unexpectedly, storytelling and historical preservation could transform dramatically. Humanity's tales might no longer be bound to physical places, but instead, we might share experiences and histories in a cosmic context. Picture this: historians and storytellers crafting narratives that intertwine the Earth's history with the cosmic journey of humanity. They would document how we navigated the challenges of space travel, the triumphs of discovery, and the evolution of our civilization in a shared universe. As we inhabit different planets or moons, local legends could emerge, reflecting the unique environments and challenges faced in these new worlds. Stories of survival, exploration, and connection could form the bedrock of culture in a cosmic society. For instance, within a colony on a distant planet, inhabitants might tell tales of the first settlers who braved the unknown, weaving in elements of their surroundings, their landscapes, climates, and even alien encounters into their lore. Preservation of this cosmic history would rely heavily on advanced technologies. Imagine digital archives floating around space stations, storing not only texts and images, but also virtual experiences. Future generations could relive the first moments on Mars or glimpse the beauty of distant galaxies through interactive narratives. With temporal distortion near massive cosmic objects, some may even view historical events as they unfolded, adding a new dimension to facts and figures. Storytelling could become a collective endeavor, with individuals from diverse backgrounds and homes contributing to the narrative tapestry. Manners of expression might stretch from traditional art to holographic presentations and immersive experiences, allowing a richer connection to the past and present. In this cosmic narrative, the essence of humanity, our dreams, struggles, and creativity, would grow even more profound, echoing through the stars, reflecting our journey as a species learning to navigate not just our world, but the universe itself. If the universe had begun just a fraction hotter than it did, the implications could be vast and transformative. To envision this, let's think about the conditions that exist immediately after the Big Bang, when temperatures soared high enough to create fundamental particles in a dense, fiery landscape. An increase in temperature at that stage could have altered the behavior of these particles. In this hotter scenario, energy levels would have been different, influencing how particles interacted with each other. For instance, fundamental forces, such as gravity and electromagnetism, might have produced stronger effects, leading to different outcomes for how matter formed. When particles combine to create atoms, a process we refer to as nucleosynthesis, higher temperatures could have resulted in a greater abundance of heavier elements. These elements are crucial for forming stars and planets. Moreover, changes in temperature could affect the expansion rate of the universe. A hotter start might have caused the universe to expand more rapidly or slow down based on the balance of forces at play and the amounts of dark energy present. This would dramatically influence the distribution and structure of galaxies, potentially leading to entirely different cosmic architectures. Additionally, the concept of dimensions or even alternate universes arises from the idea of inflation, a rapid expansion phase that occurred just after the Big Bang. If our universe had launched from a slightly more energetic state, it's conceivable that the dynamics of inflation could create different pathways for various regions of the universe. Some areas might cool faster than others, possibly giving rise to pocket universes, regions where the laws of physics differ subtly or significantly from our own. In this hypothetical universe, even the nature of dark matter and dark energy, both of which remain poorly understood, might change, leading to altered gravitational behaviors and different galactic formations. Thus, if the universe had kicked off with just a touch more heat, we could find ourselves in a reality with completely new fundamental forces, distinct cosmic structures, and possibly numerous other dimensions or universes, each unfolding in unpredictable ways. The idea of exploring space and encountering unknown phenomena has inspired countless narratives throughout history. Cultures around the world have woven tales of celestial journeys, using the stars as symbols of aspiration, wonder, and sometimes caution. From ancient myths to modern science fiction, these stories serve different purposes. They explore human curiosity, our quest for knowledge, and the moral implications of our technological advancements. One compelling narrative might center around a brave explorer who ventures into the depths of space in search of a new home for humanity. This character could encounter alien civilizations who have their own legends and histories. Their interactions could revolve around shared knowledge and cultural exchanges, emphasizing themes of unity and cooperation despite vast differences. This scenario lends itself to tales where diverse beings find common ground, showcasing how collaboration can lead to survival and mutual growth. Alternatively, a story could delve into an advanced society that exploits its technological prowess to dominate interstellar resources. This cautionary tale might reflect on the dangers of hubris, echoing warnings of ecological disaster found in various cultures. Here, the narrative could follow a group of renegades striving to reclaim their freedom and restore balance, highlighting the consequences of unchecked ambitions. Another fascinating approach would focus on a cosmic phenomenon, such as a black hole or a supernova, as a character in its own right. This entity could embody transformation and transition, serving as a backdrop for stories of personal growth. As characters face the unknown, they could learn important lessons about letting go, embracing change, and the impermanence of existence across cultures. These different narratives could resonate through various art forms, from films and television series to novels and oral traditions. They would not just entertain but also provoke thought about our place in the universe and the relationships we foster, whether on Earth or among the stars. In every telling, the essence of the human experience is revealed, a blend of ambition, fear, connection, and the endless pursuit of understanding what lies beyond our world. Dreams, art, and literature serve as windows into the human experience, reflecting not only our inner thoughts and emotions, but also the vast universe we inhabit. When we gaze at the night sky or ponder the mysteries of space, these forms of expression encapsulate the feelings evoked by such wonders. They can depict the awe we feel before the stars, the fear of the unknown, or the profound questions about our existence in an expansive cosmos. In dreams, our subconscious mind often grapples with these cosmic themes. We might find ourselves soaring through the cosmos, exploring alien worlds, or conversing with distant beings. Such dream imagery captures the essence of our quest for understanding beyond our reality, showcasing our desire to connect with something greater than ourselves. This exploration reveals both imaginative scenarios and deep-seated anxieties about the vastness of space and our place within it. Art artists, whether through painting, sculpture, or performance, commonly channel the universe's grandeur into tangible works. A vivid portrayal of a swirling galaxy, or an abstract representation of cosmic phenomena, invites viewers to engage with the mysteries of the universe visually. These pieces can symbolize beauty and chaos, stirring emotions that resonate with our experiences as human beings navigating life's uncertainties amidst an enormous universe. Literature, too, wrestles with the complexities of existence. Authors and poets weave tales that reflect humanity's relationship with the cosmos. Stories of explorers venturing into the unknown mirror our yearning to understand what lies beyond our planet, often contrasting human emotions with the cold, indifferent nature of space. Through characters facing extraordinary challenges, literature explores themes such as isolation, discovery, and the longing for connection in a seemingly infinite expanse. In all these ways, dreams, art, and literature not only reflect our unique challenges, but also illuminate the wonders of the universe, encouraging us to ponder our origins, mission, and future within this vast cosmic tapestry. They bridge the gap between our everyday reality and the extraordinary possibilities that the universe holds, reminding us that we are part of something much larger and that our imaginations are the tools to explore it. In a universe that began with extreme heat, the role of chance becomes fascinatingly significant in shaping its structures and phenomena. Right after the Big Bang, the universe was a dense ball of energy where particles were constantly colliding, interacting, and forming in a state of chaos. This intense environment is a playground for probabilities where random events can lead to ordered structures over time. As the universe cooled, particles began to combine into hydrogen and helium atoms, but how and where this happened wasn't uniform. The vastness of space allowed for regions of slightly varying densities. These differences, brought about by chance, meant that some areas began to attract more matter due to gravity, leading to clumps that eventually formed stars and galaxies. If one region had a little more mass than surrounding areas, it could grow denser, pulling in more particles while its neighbors remained sparse. These random fluctuations in density had long-term effects, influencing not just where galaxies would form, but also the types of stars these galaxies would contain. As stars evolved and ultimately exploded, they scattered heavier elements across space, enriching the cosmic material. The specific pathways these processes took were not predetermined. Instead, they were influenced by countless chance interactions throughout time. Even the formation of planets is a product of random events. The debris left over from star creation, known as the protoplanetary disk, swirls around stars and slowly coalesces into planets. The size, composition, and orbits of these planets emerge not from strict rules, but from a series of fortunate occurrences and random interactions of material. While the fundamental laws of physics govern behavior in the universe, the emergence of complex structures is deeply intertwined with chance. It teaches us that from randomness, order can arise, and this interplay of probability continues to shape the cosmos around us, influencing everything from planetary climates to the potential for life itself. Chaos theory explores how small changes in initial conditions can lead to vastly different outcomes in complex systems. This concept is crucial when considering the evolution of an alternate universe. Imagine a game of dominoes lined up in a perfect row. If you push just one, it may seem like a small act, but the resulting cascade can create a chain reaction that changes the entire arrangement. In the context of an alternate universe, even the tiniest variations in its initial state, like the amount of matter or the strength of forces at play, could lead to entirely different evolutionary paths. For example, a minor difference in the energy levels present during the universe's formation could result in a dramatically varied structure of galaxies, stars, and planets. This means that chaos theory can provide insights into the unpredictable nature of cosmic events and the development of complex systems. These unpredictable outcomes may help explain phenomena that appear random in our own universe. By applying chaos theory, scientists can develop models that simulate different scenarios, understanding how these initial variations create ripples throughout the cosmos. This approach allows for predictions that consider a vast range of possibilities, revealing the intricate dance of order and disorder shaping the fabric of an alternate universe's evolution. In the vast expanse of our universe, random events can transform from simple occurrences into moments of profound significance. Think of the universe as a grand tapestry, where each thread represents a different event or action. Sometimes the threads weave together in unexpected ways, creating patterns and connections that were not apparent at first. For instance, consider how the unpredictable nature of cosmic events, such as a nearby supernova exploding, can influence the environment of a planetary system. This explosion releases massive amounts of energy and particles that can potentially alter the chemical makeup of nearby planets, sparking new processes that could lead to the development of life. What begins as a chance occurrence in the cosmos suddenly takes on immense importance, affecting the trajectory of worlds millions of miles away. Similarly, in our own lives, randomness often intersects with choice. A chance meeting with someone could lead to a partnership or friendship that changes your life path. In the universe, the laws of physics also introduce elements of unpredictability, especially with phenomena like quantum mechanics, where tiny particles behave in ways that seem entirely based on chance rather than predictability. This interplay of randomness and significance becomes even more interesting on a cosmic scale when we consider the larger implications of chaos theory. Tiny changes in one part of a system can lead to vast differences in another, much like how the flap of a butterfly's wings might influence weather patterns far away. The unpredictability of random events can lead to unique, life-altering scenarios, reminding us that the universe thrives on complexity and surprises. What initially seems random can form the basis for new opportunities, discoveries, and even entire ecosystems. In an altered universe, beings embarking on a journey of discovery would face unique challenges and opportunities that differ significantly from our own experiences. These explorers might encounter environments governed by different physical laws, leading to perceptions and reactions that are not familiar. For instance, gravity could vary in strength, affecting how they move and interact with their surroundings. This would demand adaptations in their bodies and technologies to successfully navigate new terrains. Moreover, the sense of time could be altered, influencing how these beings experience events. A day might feel longer or shorter, changing their concept of what progress means during their explorations. Communication could also be impacted. If sound behaves differently, they might develop alternative ways to exchange information, perhaps relying more heavily on visual cues or light-based signals. The mysteries they uncover would likely be unlike anything we can imagine. With different elemental compositions or chemical interactions, previously known materials might behave in surprising ways. This could lead to the creation of entirely new technologies or discoveries, sparking innovation driven by the challenges of their universe. As they explore, these beings would form philosophical concepts based on their unique experiences and surroundings. Their understanding of life, existence, and their place in the universe could shift dramatically, fostering a sense of wonder and curiosity that is shaped by the very nature of their altered reality. Their journey would be marked not only by discovery, but by a profound transformation of how they think, feel, and interact with the universe around them. Each step into the unknown would offer both awe and uncertainty, inviting endless questions about the nature of existence itself. The concepts of fate and destiny may appear similar, but they introduce intriguing variations in the narratives of civilizations throughout the universe. Fate can be understood as a predetermined course of events, suggesting that the path of a civilization is locked in place, guided by forces beyond its control. This idea evokes images of civilizations that might struggle against a set trajectory, where their actions seem to echo a grand plan, resulting in a sense of inevitability surrounding their rise and fall. On the other hand, destiny carries a more flexible interpretation. It implies potentialities that can be shaped by the choices made by individuals and societies. In this view, civilizations could steer their own paths through decision-making and innovation, potentially changing the course of their existence through collective will and creativity. Thus, destiny portrays a narrative where agency matters, emphasizing the power of choice, learning from failure, and adapting to the challenges of the universe. When we consider how these forces play out in different civilizations, we can envision diverse outcomes. For a society believing in fate, there could be a sense of resignation or acceptance, leading to unique cultural expressions, rituals, and philosophies aimed at making peace with their perceived predestined journey. Conversely, a society that embraces destiny may often find itself on the cutting edge of exploration and progress, driven by ambition and the idea that their future is not pre-written, but rather is a blank slate that they continuously fill with their actions. Imagining how different civilizations interact with these concepts opens a window into a range of technological advancements, cultural narratives, conflicts, and resolutions. They could either be facing their fateful challenges with stoicism or forging their own way through the stars, each uniquely shaped by their existential beliefs. In this vast universe, the interplay between fate and destiny could lead civilizations to experiences that are equally profound, yet entirely distinct, shaping their stories for generations to come. Throughout history, discoveries in science have fundamentally reshaped our understanding of the universe. Consider the moment when humanity first turned to the stars through a telescope. By peering into the night sky, we uncovered moons orbiting other planets, which challenged the belief that Earth was the center of everything. This shift opened the door to a universe much larger and more complex than previously imagined. Now, imagine the potential impact of discovering a new form of matter or energy, something entirely foreign to our current understanding. For instance, finding dark matter could redefine our grasp of the universe's structure. Dark matter is thought to make up a vast portion of the universe's mass, yet it's invisible and detectable only through its gravitational effects. If scientists were able to observe or create a form of dark matter, it would challenge our existing frameworks of physics and cosmology. Another revolutionary discovery could involve the existence of extraterrestrial life. Imagine a mission finding microbial life on another planet or in the ice of a moon. This would not only confirm that we are not alone, but also lead to deep questions about life's origins, its potential diversity, and what it means for human existence and philosophy. Then there are phenomena like gravitational waves, which were only recently detected. These ripples in space-time offer a new way of looking at cosmic events, such as colliding black holes. The ability to perceive the universe through this lens opens pathways to understanding events that were previously invisible to us, reshaping our understanding of gravity and the very fabric of reality. Additionally, advancements in quantum physics could fundamentally alter our grasp of reality. Concepts like quantum entanglement, the idea that particles can be instantaneously connected over vast distances, challenge our traditional views of space and separateness. If harnessed, such understanding could revolutionize technology, communication, and our understanding of the universe itself. These legendary discoveries have the power to transform our very identity within the cosmos, pushing the boundaries of knowledge and redefining humanity's quest for meaning in the vastness of space. Imagine a civilization nestled within a planet's orbit, using the gravitational forces of nearby celestial bodies to their advantage. Just as a skilled surfer rides the waves, these beings could harness the pull of gravity to facilitate movement in space. By aligning their ships with the gravitational fields of larger planets, they could achieve greater speeds without expending much energy. This technique, known as gravitational slingshot, allows them to travel vast distances by carefully selecting their path through the cosmos, utilizing the forces around them to propel themselves forward. Now, consider how heat from stars influences life on a planet. These civilizations might engineer their habitats to capture and store the warmth emanating from their sun. This could involve reflective materials that direct sunlight into their structures, keeping them comfortable even when the star sets. They could build systems that convert this heat into energy, powering their technology and supporting their way of life. In environments with extreme temperatures, they might develop mechanisms to shield themselves from excessive heat or to concentrate it for their use, depending on their needs. Furthermore, if these beings were advanced enough, they could even experiment with manipulating these cosmic forces. Imagine the potential of creating artificial gravity fields to stabilize their ships or control environmental conditions within their settlements. Manipulating heat could allow them to engineer climates that support agriculture or to create energy-efficient systems. In this vast universe, where gravity and heat are fundamental forces that shape the lives of cosmic entities, the possibilities for innovation and adaptation are immense. Each civilization could find unique ways to interact with these forces, allowing them to thrive in the dynamic dance of the cosmos. As we gaze into the vastness of space, the possibility of novel cosmic forces arising is both thrilling and mind-bending. The universe is an ever-evolving tapestry, continually shaping and reshaping itself. While we currently understand many fundamental forces such as gravity and electromagnetism, space may hide mysteries that remain undiscovered. Consider dark energy, for instance. This enigmatic force is responsible for the accelerated expansion of the universe. Scientists are still working to unravel its nature, leading to questions about what this force really is and whether it is merely a facet of the universe's intricate design or something entirely new. If we could better comprehend dark energy, it might require us to rethink the very fabric of physics as we know it. Further, the study of cosmic phenomena like neutron stars or black holes reveals forces acting in extreme conditions. These environments push the rules of physics to their limits. The interactions happening in such regions could lead to the emergence of new forces or behaviors that demand a revised understanding of the laws of nature. If a unique cosmic force were to emerge, it might challenge our existing frameworks, leading scientists to develop innovative theories and tools to study them. As exploration advances, with missions to distant galaxies or deeper studies of cosmic microwave background radiation, we are likely to encounter phenomena that stretch our imagination. Each discovery brings with it the potential for new forces, each with its own characteristics, and possibly even implications for advanced technologies that harness these unknown energies. In a sense, the universe is a grand experiment, and each new layer we peel back holds the promise of understanding phenomena that until now have remained beyond our grasp. This adventure into the unknown not only enriches science but also opens doors to new possibilities that might fundamentally alter our mastery of the cosmos. To coexist with the vast and often unpredictable forces of the universe, both in the context of space exploration and potential encounters with cosmic phenomena, humans would need to develop a range of strategic and tactical adaptations. First and foremost, creating robust technology that can withstand extreme conditions is essential. This includes spacecraft designed to endure intense radiation, powerful gravitational fields, and significant temperature variations. Utilizing materials that are both lightweight and incredibly durable would be key in this endeavor. Next, employing advanced navigation systems would play a crucial role. These systems would need to calculate safe paths through environments filled with asteroids, comets, or even unknown cosmic threats. Imagine spacecraft equipped with sensors that can detect changes in the environment ahead, allowing for real-time adjustments to travel routes. Additionally, the idea of collaboration becomes paramount. Just as nations work together on Earth, space missions might require partnerships between countries, sharing technology and knowledge to enhance safety and efficiency. This collaborative approach could involve international guidelines for responding to potential dangers, creating a unified front that can provide support when unforeseen circumstances arise. Training and preparation also cannot be overlooked. Astronauts and crew members would need to undergo rigorous simulations to prepare for unexpected events, akin to emergency drills on Earth. This training would ensure that they are ready to respond swiftly and effectively to any situation they might face in the unpredictable environment of space. Finally, embracing adaptability and resilience in the face of new discoveries would be vital. The cosmos can surprise even the most advanced technology and well-laid plans. By fostering a mindset that allows for flexible responses to new challenges, humanity can better navigate the complexities of coexisting with the forces of the universe, making each venture into space a little safer and more informed. Imagine a vast ocean, where each droplet represents a possible timeline. All these droplets start in the same area, created from similar conditions like waves stirring the water. Initially, they may appear identical, but small disturbances like a gentle breeze or an insect landing on the surface create tiny variations in their paths. These variations can have profound effects over time. In the realm of parallel timelines, even the slightest difference can lead to dramatically different outcomes. For example, if two timelines begin in the same situation, but in one, a person chooses to turn left at a fork in the road, while in the other, they turn right, these small choices can eventually result in entirely different lives unfolding. As each timeline continues to separate from its neighbor, the differences accumulate. Relationships might form or dissolve, opportunities may be seized or neglected. Over generations, what began as small deviations can result in vastly different societies, cultures, and realities. The original event is like a seed that grows into a tree, where even a minor twist in the initial few inches of growth leads to entirely different branches and fruits later on. The idea of parallel timelines highlights how interconnected and complex our universe is. It suggests that all futures are woven together, yet distinct paths emerge from the tiniest of changes, showcasing the intricate dance of possibility and choice in the fabric of reality. The concept of timelines, particularly in relation to changes in cosmic temperatures, invites us to delve into the idea of parallel universes or alternate realities. When we talk about cosmic temperatures, we're often referring to the temperature of the universe, which has evolved since the Big Bang. This temperature influences everything from the formation of galaxies to the development of life. If we imagine different timelines where cosmic temperatures are slightly altered, we could envision a scenario similar to how different environments on Earth result in diverse species. For instance, a cooler cosmos might slow the process of star formation, potentially leading to fewer stars and thus fewer habitable planets. In contrast, a warmer universe could facilitate a faster pace of stellar evolution, creating a rich tapestry of life forms in astoundingly different ecological settings. As these timelines adapt to their respective temperatures, possible interactions could emerge. Entities or beings that evolve within one timeline might experience the effects of a more stable climate, while those in another might face extreme conditions that drive rapid adaptation. The exchanges between these timelines could involve knowledge or technology crossed through theoretical portals, akin to stories of parallel worlds colliding or interacting. An intriguing aspect of this interaction might involve changes in the fundamental laws of physics due to temperature differences. For instance, a colder universe might have stronger gravitational forces because matter is more densely packed, while a hotter universe may experience lighter particles flitting about more freely. These differences wouldn't just impact how life develops. They would create entirely different sets of physical realities where timelines might see variations in the very fabric of existence, creating realms where space and time operate under different rules. As these timelines adapt and evolve, there may be moments when they brush against one another. This could lead to exchanges or even conflicts arising from fundamentally different forms of matter, energy, and the laws governing their existence. The interplay of such varied cosmic temperatures can spark discussions about the resilience and adaptability of life and the constants of nature that bind or separate these realities. Thus, envisioning these parallel timelines prompts fascinating considerations and possibilities regarding the nature of existence itself. The study of parallel universes is a fascinating and speculative field that blends science, philosophy, and imagination. To explore the intricate differences in parallel universes, researchers can develop a variety of methodologies that are grounded in both theoretical physics and imaginative inquiry. One promising approach is through advanced computer simulations. Just as scientists use computer models to understand complex systems on Earth, they can create simulations that mimic the conditions of different universes. These models could explore various physical laws, constants, and initial conditions, allowing researchers to visualize how small changes might lead to vastly different outcomes. This method helps reveal the potential diversity of realities, illustrating scenarios where, for instance, gravity behaves differently or the forces of nature fluctuate in unexpected ways. Additionally, researchers might employ quantum field theory, which explores the fundamental particles and forces that make up the universe. By manipulating the principles of this theory, scientists can theoretically predict how alternate realities could function. Investigating the implications of quantum mechanics, especially phenomena like entanglement or superposition, may provide insights into how parallel universes interact or overlap with our own. By understanding these principles, one could hypothesize about the conditions necessary for a parallel universe to exist. Experimentation with cosmic phenomena could also yield valuable data. For example, scientists might closely study cosmic microwave background radiation, which is the afterglow of the Big Bang. This radiation carries clues about the early universe and might, in some scenarios, hint at the existence of other neighboring universes. Observations of strange cosmic events, such as collisions between galaxies or the behavior of dark matter, could potentially offer indirect evidence of alternate realities. Furthermore, interdisciplinary collaboration can enhance the exploration of parallel universes. Physicists might work alongside philosophers and cognitive scientists to examine the implications of parallel universes on consciousness and perception. Understanding how humans perceive reality could become central to refining our theories about alternate universes, providing a more holistic view of existence across different realms. All these methodologies highlight the complexity of studying parallel universes. While the direct observation of alternate realities remains out of reach, theoretical frameworks and creative scientific practices can forge pathways to understanding what might lie beyond our own universe. Such exploration fuels curiosity and expands our comprehension of reality, opening up new realms of thought about existence itself. In a universe characterized by a higher thermal baseline, energy systems and networks would adapt significantly to accommodate the surrounding conditions. Essentially, a higher thermal baseline means that the average temperature of the environment is hotter, which would influence every aspect of energy generation and distribution. Firstly, conventional energy sources such as fossil fuels or solar power would operate under different efficiencies. Higher ambient temperatures might enhance certain energy production methods, like those using heat, but could hamper others that rely on cooler conditions. For example, traditional photovoltaic solar panels would face challenges in converting sunlight to electricity because their efficiency typically declines as temperatures rise. Therefore, innovative cooling technologies or new types of solar cells designed to perform well in higher temperatures would become vital. Moreover, energy transmission networks would also undergo transformations. In hotter environments, loss of energy during transmission could become more pronounced. As wires heat up, they may become less efficient at conducting electricity, which would lead to a need for new materials or designs that can minimize resistance and waste. Additionally, more efficient methods for energy storage would be required, as batteries and other storage systems might discharge energy more rapidly in higher temperatures. Increased demand for cooling solutions would emerge in this heat-dominated universe. Energy systems would likely focus on developing advanced heat management technologies that could handle elevated temperatures. For instance, district cooling networks might become more prevalent, which distribute cooling through a central system rather than relying on individual installations. Finally, the integration of renewable energy sources would necessitate new approaches. The need to diversify energy generation would be heightened, leading to investment in geothermal and ocean thermal energy, tapping into the natural heat of the earth and oceans respectively. These methods could leverage the higher thermal environment to create sustainable energy systems. A universe with a higher thermal baseline would drive innovation in energy production, transmission, storage, and utilization, forcing scientists and engineers to rethink existing technologies and embrace creative solutions to harness energy efficiently in a warmer world. Energy recycling and conversion processes can indeed differ significantly in how they operate and in their effectiveness. To grasp this, imagine energy like a flowing river that can take various paths. Energy recycling involves taking energy that has already been used, such as waste heat or solar power, and directing it back into the system for reuse. This is akin to rerouting part of the river back upstream to ensure it flows again effectively rather than just letting it get wasted. On the other hand, energy conversion refers to the process of changing energy from one form to another. For example, solar panels convert sunlight into electricity. This energy transformation can take multiple forms, like turning mechanical energy into electrical energy with a generator, or converting chemical energy from fuels into motion in cars. Each method has its own efficiency levels, costs, and environmental impacts. The dramatic differences arise in how much energy is lost in each process. While energy recycling typically aims to minimize waste and improve efficiency, conversion processes may inherently involve loss, as not all energy will be transformed into useful work. Additionally, the technologies used for recycling, like heat exchangers, and the ones used for conversion, like turbines or batteries, are often designed specifically for their tasks, which shapes their effectiveness. Understanding these differences highlights the importance of improving both recycling and conversion technologies. As we strive for a more sustainable future, finding ways to enhance energy recycling can help us use our resources more wisely, while advanced conversion techniques can enable us to harness energy in cleaner and more efficient ways. New energy sources offer exciting possibilities to push beyond our current limitations in several key ways. First, they could provide cleaner and more sustainable power. Traditional energy sources like fossil fuels generate pollution and contribute to climate change. In contrast, renewable sources such as solar, wind, and geothermal energy harness natural processes to produce electricity without damaging the environment. This shift not only protects our planet, but also ensures that future generations have the resources they need. Moreover, advanced energy technologies like nuclear fusion hold the promise of providing immense amounts of energy with minimal waste. Fusion, which powers the sun, has the potential to deliver a nearly limitless energy supply if we can harness it on Earth. The advantage is that it uses abundant fuel sources and safely produces power without the long-lived radioactive waste associated with current nuclear fission reactors. Additionally, breakthroughs in energy storage systems allow us to efficiently capture and store energy for later use, overcoming one of the biggest challenges in relying on intermittent energy sources like solar and wind. When the sun isn't shining or the wind isn't blowing, these technologies can make energy available on demand. This reliability can transform how we power our homes, industries, and even vehicles. By diversifying our energy portfolio with these innovative solutions, we can enhance energy security and independence, reduce reliance on imports, and foster economic growth through the development of new technologies and jobs within these industries. Ultimately, new energy sources could not only help us meet our current demands, but also pave the way for a more sustainable and resilient future. A hotter cosmic beginning would fundamentally reshape the conditions of the universe as we know it. When considering the early universe, it was initially a hot and dense environment, teeming with energy. If this initial state were even hotter, the implications would be vast. In a scorching universe, particles would move rapidly and collide with great force. This heightened energy could lead to a more chaotic environment, affecting the formation of fundamental elements. Hydrogen and helium, the building blocks of stars and galaxies, might be produced differently or not at all, altering the chemical makeup of the cosmos. As stars began to form, they would likely be hotter and possibly larger than the ones we see today. These high-energy stars would emit intense radiation, influencing their surrounding spaces. Such radiation affects how planets form and whether they can maintain atmospheres. In the vicinity of these fiery stars, habitable zones, regions where conditions might support life, could be pushed much farther away. On a planetary scale, worlds would face extreme environments. If planets formed around these stars, their surfaces might be constantly battered by radiation, leading to harsh atmospheres that could strip away the possibility for life as we understand it. Water, considered essential for life, could evaporate, leaving behind arid and barren landscapes. Moreover, with the overall temperature of the universe being higher, cosmic events like supernovae, which are explosive deaths of stars, would occur more frequently and with greater intensity. These explosions would release significant amounts of energy and material that could influence nearby star systems, potentially leading to bursts of star formation or creating hostile conditions that could extinguish developing life. A hotter cosmic start might foster an environment where life is extremely unlikely, emphasizing the delicate balance that allows for the emergence of life in our current, more temperate universe. While some planets might still retain a semblance of habitable conditions, many would likely transform into inhospitable environments, reshaping the narrative of life's potential across the cosmos. Space is a constantly changing environment, and its habitability can be influenced by various factors, including cosmic radiation and thermal dynamics. Cosmic radiation comes from numerous sources, including the Sun, supernova explosions, and distant galaxies. As these high-energy particles travel through space, they can affect the conditions on planets and their potential for supporting life. If cosmic radiation levels increase, for instance, they could pose a greater threat to any living organisms, potentially disrupting biological processes and increasing mutation rates. High radiation environments also pose challenges for space travel and long-term habitation beyond our planet. Thermal dynamics, which deal with the transfer of heat, play a significant role in the overall conditions of space. As the Sun undergoes its natural cycles, the levels of radiation and heat it emits can change. These variations can lead to fluctuations in temperatures on nearby planets or moons. If a planet's surface temperature rises or falls significantly, it can affect the stability of liquid water, which is essential for life as we know it. Additionally, as cosmic events occur, such as the formation of new stars or the expansion of galaxies, the configuration of cosmic matter and energy shifts. This can either shelter or expose certain regions of space to more radiation or extreme temperatures. For example, if a nearby star goes supernova, the explosion generates a burst of cosmic radiation that can dramatically alter conditions in surrounding areas. In conclusion, shifts in cosmic radiation and thermal dynamics can make space more or less hospitable. These changes can directly impact the potential for life on planets and influence human exploration and habitation beyond Earth. As we continue to study the cosmos, understanding these effects will be essential for ensuring safe travels and perhaps even future colonization of other worlds. Life in the universe showcases incredible adaptability, driven by the need to survive in various environments. Each planet or moon has its unique set of conditions, and organisms may innovate in fascinating ways. For instance, on a planet with extreme temperatures, whether scorching hot or frigidly cold, life forms might evolve reflective surfaces or thick insulating layers. These adaptations can help them regulate their body temperature, allowing them to thrive where others might not survive. In environments rich in radiation, some organisms could develop protective shielding, like natural armor that absorbs harmful rays. Think of shells or skins that are tough enough to minimize damage from cosmic radiation or stellar activity. Similarly, life forms in dark, turbulent regions, such as beneath the thick atmospheres of gas giants, might harness bioluminescence, using light not only to attract mates, but also to lure prey in utterly dark landscapes. Aquatic life may also showcase remarkable adaptations in extreme pressure situations, such as deep oceanic trenches. Here, they might develop flexible bodies that can withstand crushing forces, along with specialized organs capable of withstanding the cold and high-pressure conditions. Some creatures may even use biochemical processes to produce energy, allowing them to live where sunlight cannot penetrate. On planets with scarce resources, innovative strategies might emerge for obtaining food and water. Life forms could evolve symbiotic relationships, working together with other species to access nutrients. Furthermore, organisms could become capable of storing resources efficiently, using special tissues or organs to retain water during periods of drought. These examples highlight the brilliance of evolution and the potential for life to find a way to not only survive, but thrive in the unlikeliest of environments across the universe. Each unique adaptation ultimately underscores the resilience and ingenuity of life itself, hinting at the endless possibilities waiting to be discovered. Imagine a universe where the rules of temperature, much like here, follow basic physical principles. In this counterpart universe, suppose the average temperature is lower by a specific fraction compared to our own. This change in temperature would have profound effects on the environment and the life forms within it. In our universe, temperature is crucial for determining the state of matter. Water, for instance, exists as a liquid at temperatures just above freezing, but it freezes solid at lower temperatures. In this parallel universe, if temperatures are significantly lower, water might remain frozen for most of the time. This would create a very different ecological environment, likely dominated by ice and cold-resistant organisms resembling highly adapted forms of life. Moreover, chemical reactions, including those necessary for life, slow down as temperatures decrease. This means that biochemical processes would be different, potentially leading to life forms with slower metabolisms or entirely different ways of storing energy. The climate, too, would vary remarkably. Lower temperatures would impact weather patterns, leading perhaps to longer winters and brief summers. The landscape might feature vast stretches of ice, perhaps with some regions that could support life when conditions allow. What's fascinating is this. While the laws of physics remain constant, how they manifest differs drastically in a cooler universe. It paints a picture of a world that, while similar in structure, is fundamentally altered in characteristics, from the simplest physical interactions to the complexity of life. Each counterpart universe presents a unique reflection of how slight adjustments can lead to significant changes in the cosmos. When we think about the possibility of opposing universes interacting, we enter a realm filled with intriguing scenarios. Imagine two parallel universes, each with its own set of physical laws, histories, and realities. The most captivating idea is that these universes could occasionally overlap or communicate in some way, leading to unexpected interactions. One possibility is that events in one universe could influence the other through a process similar to what scientists call quantum entanglement. This phenomenon suggests that particles can be connected even when separated by vast distances, so if one changes, the other does too. In the context of opposing universes, it raises questions about whether actions taken in one universe might resonate through this connection to affect the other, creating ripple-like effects. We could also consider the exchange of information. In this scenario, forms of energy or matter might pass through thin barriers between the universes. This exchange could spark entirely new phenomena, uniting elements from both realities to create something unique. Imagine how different biological or technological advancements in one universe might enter another, altering its trajectory. Another fascinating idea is the concept of merging or colliding universes. If the boundaries between them blur, we might witness a spectacular fusion of the two, leading to a new reality filled with hybrid characteristics. Such events might offer new forms of life or unusual gravitational effects, reshaping everything we know. However, while these interactions may sound exciting, they come with a host of uncertainties. The fundamental rules governing one universe might not align with those of the other, leading to chaotic or unpredictable outcomes. The nature of existence itself could shift dramatically, and the result might be something we cannot even begin to comprehend. The interaction possibilities between opposing universes stretch the imagination and challenge our understanding of reality. Each scenario reveals that the universe, or rather the multiverse, may hold complexities that push the limits of our knowledge and creativity. Civilizations exploring the idea of dual or mirrored realities might grapple with profound questions about their own existence. Imagine a world where different versions of reality coexist, much like how reflections appear in a mirror. Each civilization could have a set of beliefs shaped by their understanding of these realities. They might wonder if these mirrored realms are parallel to their own, each holding different outcomes and possibilities. The pursuit of knowledge in such a context would likely lead to philosophical explorations. Societies could develop concepts of identity, purpose, and fate through the lens of these dual realities. They might ask whether their actions in one reality impact the other, or if both exist independently. This inquiry could spark debates among scholars, artists, and the religious, influencing culture and societal norms profoundly. To explore these realities, civilizations might turn to cutting-edge science and technology. They could build advanced instruments designed to detect and analyze phenomena that hint at these mirrored realms. Concepts like quantum physics, which already hints at multiple outcomes existing simultaneously, might serve as a foundation for their studies. Storytelling could also play a significant role in how civilizations interpret their existence within these realities. Myths and narratives could evolve to reflect their understanding of dualities, sparking imagination about their relationships with alternate versions of themselves. This might lead to rich traditions of art, literature, and media that depict the struggles and triumphs of encounters with alternate realities. In navigating these dual worlds, humans may also face ethical dilemmas. Decision-making could become increasingly complex and layered as they consider not just the impact of their choices but also the potential ripple effects across parallel existences. The nature of free will versus determinism might become a central philosophical question, captivating minds for generations. Ultimately, as civilizations engage with the concept of dual realities, they would embark on a journey not just of exploration, but also of self-discovery. Through examining reflections of themselves in alternate realms, they could uncover deeper truths about existence, purpose, and interconnectedness in a vast, complex universe. In a hotter universe, the way we forecast and predict cosmic phenomena would undergo significant changes due to the altered behavior of matter and energy. Imagine a universe gradually heating up, where stars burn hotter and faster. In this scenario, the life cycle of stars would be shortened. They would consume their nuclear fuel more rapidly, leading to more frequent supernova explosions. This celestial clock speeding up would make it crucial for astronomers to adjust their models accordingly to anticipate these dramatic events. As temperatures rise, gas and dust in space would behave differently. Hotter conditions can lead to increased activity in star formation regions. The gas clouds that typically collapse under gravity to form new stars would become more turbulent due to enhanced thermal energy, potentially slowing down star formation despite the increased heat. Predicting star birth rates would require new models that account for this chaotic behavior. Additionally, a hotter universe affects galaxy interactions. Galaxies could experience more vigorous collisions and mergers as gravitational forces act more intensely in hotter conditions. This interplay could lead to the rapid evolution of galaxies, making predictions about their structure and behavior much more complex. On the broader scale, cosmic phenomena such as the cosmic microwave background, essentially the heat radiation left over from the Big Bang, would also reveal different characteristics. As the universe heats up, scientists would need to refine their interpretations of this fossil radiation, which provides crucial information about the universe's early moments. A hotter universe would require scientists to rethink existing theories and develop new predictive models to keep pace with the dynamic changes occurring across cosmic scales. The fundamental laws of physics would still guide our understanding, but the specific applications of those principles would evolve to fit the new environmental conditions. As we look to the future of astronomy, new models for predicting cosmic events will likely combine advanced technology with innovative data analysis techniques. Traditionally, scientists have relied on telescopes and direct observations to track celestial bodies and phenomena. However, as we gather more data from space missions and astronomers around the world, we will see a shift toward utilizing artificial intelligence and machine learning. These technologies can help analyze vast amounts of data, identifying patterns and predicting future cosmic events with increased accuracy. Additionally, integrating simulations of cosmic phenomena will become essential. Think of creating a virtual universe where scientists can manipulate variables such as gravity and density to observe potential outcomes. This method allows them to explore what might happen under various conditions, improving our understanding of events like supernovae, asteroid impacts, and even black hole formations. Moreover, interdisciplinary approaches that combine insights from physics, mathematics, and computer science will pave the way for more refined forecasting models. By developing equations that relate to gravitational effects, energy states, and elemental compositions, researchers can create mathematical constructs that predict behaviors in complex systems. As we continue to discover new celestial bodies and phenomena, these models will also evolve. Each new observation can serve as feedback, helping scientists refine their predictions. This adaptive approach promises to make anticipating cosmic events more precise, transforming our understanding of the universe and its timelines. With these advancements, we may soon be able to foresee events that were previously considered unpredictable, adding a new layer to our comprehension of the cosmos. Predictive technologies are increasingly important in understanding the complexities of our changing environment, especially when thermal conditions fluctuate. These technologies often use vast amounts of data from various sources to make educated guesses about future events or conditions. To adapt to altered thermal conditions, predictive technologies start by gathering extensive historical data. This might include temperature records, humidity levels, and seasonal variations. By analyzing this information, they can identify patterns and relationships that existed before changes began to occur. However, in the face of new and unpredictable thermal conditions, simply relying on past data isn't enough. As thermal environments change, models must be updated regularly to reflect real-time conditions. This usually involves integrating new data from a variety of sensors, such as satellites measuring surface temperatures, ground stations monitoring local weather conditions, or even smart devices that track immediate environmental changes. These inputs help create a more accurate picture of what is happening now, which is critical when predicting future outcomes. Furthermore, machine learning and artificial intelligence play vital roles in this evolution. By employing algorithms that can learn from new data continuously, these technologies gain the ability to adjust their predictions based on newly observed trends. This means they can become more effective in recognizing unusual thermal patterns, perhaps caused by climate change or human activity. As these systems learn and adapt, they can better forecast scenarios ranging from agricultural yields impacted by heat waves to urban infrastructure stressed by rising temperatures. Ultimately, by combining historical data with real-time observations and advanced learning techniques, predictive technologies can more successfully navigate and understand the complexities introduced by changing thermal conditions. This adaptability not only enhances their accuracy, but also provides essential insights for decision-making in various fields, from agriculture and energy management to disaster preparedness. As the universe continues to evolve, one of the biggest challenges we may face is dealing with rising temperatures across vast expanses of space. Creative solutions require a combination of innovation and adaptability in technology and society. One potential approach involves developing advanced materials that can reflect more sunlight, acting like a shield against the heat. These materials could be used on spacecraft or habitats, helping to keep environments cool despite external temperature increases. Another exciting avenue is the concept of space-based solar panels. Imagine a network of satellites positioned in space to capture sunlight more efficiently and then beaming that energy back to Earth. This setup could provide a limitless energy source, reducing our reliance on fossil fuels, which contribute to warming on our planet. On a larger scale, we might explore geoengineering techniques that involve altering the planet's climate deliberately. For instance, scientists could investigate methods to increase cloud coverage to reflect more sunlight away from the Earth. Yet this brings many complex implications and requires careful management to avoid unintended consequences. In addition, there's a need for a shift in how we design new structures and cities. These might incorporate natural cooling techniques, such as using trees and plants to provide shade or implementing water features to lower temperatures. By integrating nature into our urban environments, we can create spaces that naturally combat heat. On the forefront of human adaptation, developing resilient agricultural techniques will be essential. This could involve cultivating heat-resistant crop varieties and utilizing practices that conserve water effectively. As regions become hotter, communities might need to rethink how and where they grow food. Lastly, fostering a collaborative global effort is vital. Countries and organizations will need to synergize their resources and knowledge to tackle this universal challenge. By sharing innovative solutions and embracing a cooperative spirit, we can create effective strategies to both harness resources and mitigate the effects of a hotter universe. Through these combined efforts, humanity can adapt to changing conditions and thrive despite the odds. As we venture into the complexities posed by cosmic exploration, technological innovation emerges as a crucial player. In space, the environment is incredibly harsh, which necessitates advanced solutions tailored to unique challenges. For instance, the vacuum of space means that every piece of equipment must be designed to function without the support of an atmosphere. This requires materials that can endure extreme temperatures and radiation levels, while ensuring the safety of astronauts and the integrity of instruments. Consider the concept of life support systems. These systems are fundamental for allowing humans to thrive in space, recycling air and water while providing food. Innovations in closed-loop systems enable recycling of waste materials, ensuring that nothing goes to waste. This efficiency must be finely tuned, often drawing inspiration from our Earth-based technologies, yet it must function seamlessly without the constant availability of resources we take for granted. Moreover, communication technology faces its own set of demands. Signals travel at the speed of light, but due to vast distances in space, there can be significant delays. Developing communication systems that can handle this delay while maintaining reliable contact is essential. This involves using satellites and relay systems that can transmit data efficiently across light years, ensuring that teams on Earth and in space remain in constant touch. Energy generation must also adapt to cosmic requirements. Solar panels powered by sunlight can be effective, but need to be designed to collect energy in low-light conditions, such as from distant stars or during long durations of darkness. Innovative storage techniques also come into play to ensure energy is available when needed. Additionally, the need for exploration and research drives advancements in robotics and automation. Robots can go where humans cannot, enabling the exploration of distant planets and moons. These machines must be equipped with sophisticated sensors and AI systems to analyze data and make decisions on their own, reflecting the reality that in vast, uncharted territories, human direction may not always be possible. Ultimately, the technological evolution we witness in response to these cosmic scenarios showcases human ingenuity's ability to adapt. Each innovation not only meets the immediate challenges of space itself, but also serves as a testament to our desire to explore, learn, and push the boundaries of what is possible. As we continue to reach for the stars, these advances pave the way for future generations to uncover the mysteries of the universe. Artificial intelligence and synthetic organisms hold remarkable potential in adapting to and transforming our universe. Imagine living in environments that are vastly different from Earth. Extreme temperatures, toxic atmospheres, or even places without solid ground. Artificial intelligence can be the key to solving these challenges. It can analyze vast amounts of data about these environments quickly and effectively, helping us understand the conditions that exist on distant planets or moons. One significant role for AI lies in exploration. Think of robots equipped with intelligent systems that can navigate unknown planetary surfaces. These robots could make real-time decisions based on their findings, relaying essential data back to scientists on Earth and paving the way for future human exploration. Using advanced algorithms, AI can also optimize the design of habitats, ensuring that they provide essential life support while making the best use of available resources. Meanwhile, synthetic organisms could be engineered to thrive under alien conditions. Imagine organisms designed to absorb toxic gases and produce oxygen, making a hostile planet more habitable for humans. These synthetic life forms might be tailored to extract water from the atmosphere or convert local minerals into vital nutrients. This approach would not only support human life, but could also assist in creating a sustainable ecosystem on a new world. Furthermore, AI could enhance our understanding of biomes by simulating complex interactions between organisms. This knowledge can guide us in creating synthetic creatures that might collaborate with Earth species, leading to hybrid systems that are resilient and capable of flourishing in diverse environments. As we venture further into the cosmos, the collaboration between artificial intelligence and synthetic organisms will be crucial. They could enable a new era of exploration and habitation, adapting not only to survive, but also to transform and flourish in the vast, often unwelcoming universe. This partnership may ultimately redefine the very essence of what it means to exist in space, offering a glimpse into exciting possibilities for the future. The quest for understanding our universe goes far beyond mere curiosity. It has the potential to reshape civilizations in profound ways. Imagine each new discovery in space, such as understanding the formation of stars or the mechanics of black holes, inspiring people everywhere to think bigger, dream longer, and reach further. This knowledge can challenge our perspective, igniting a sense of unity as we realize we are all part of the same cosmic tapestry. As civilizations explore the cosmos, they innovate technology that enhances life on Earth. The advancements in communication, navigation, and exploration are often spawned from space research. For instance, technologies originally developed for space missions like satellite communications have revolutionized how we connect with one another. This symbiotic relationship creates a feedback loop where understanding space pushes societies to develop more sophisticated tools and solutions that, in turn, improve life on our planet. Moreover, the pursuit of cosmic understanding fosters international collaboration. Nations often come together for shared space missions, combining resources and knowledge to achieve common goals. This cooperation can lead to peaceful relations, breaking down barriers and building alliances as countries work side by side in the name of discovery. The philosophical implications are equally striking. As we learn more about the universe, such as the potential for life on other planets, our place in the cosmos becomes ever more complex. This awareness might drive humankind to prioritize sustainability and stewardship of Earth, recognizing the need to protect our home as a vital part of a larger system. Finally, the dreams of exploring other planets or even establishing colonies on distant moons can prompt new societal structures, economic models, and ethical considerations. These exciting possibilities challenge us to innovate not only in technology, but in how we define community, governance, and what it means to be part of an interstellar civilization. The pursuit of cosmic understanding doesn't merely expand our scientific knowledge. It has the power to transform societies, spark collaboration, and redefine our humanity in the grand context of the universe. The quest to understand altered cosmic conditions, such as those found in extreme environments like black holes or the early moments after the Big Bang, is filled with both significant obstacles and groundbreaking accomplishments. One major challenge is the sheer distance and inaccessibility of many of these phenomena. For example, studying a black hole is inherently difficult as they do not emit light. Their presence is usually inferred through their impact on surrounding matter, which requires sophisticated detection methods. Another critical obstacle is the extreme conditions themselves. For instance, near a black hole, the gravitational forces are so intense that they distort space and time, creating conditions that make traditional physics difficult to apply. Scientists must develop new theoretical frameworks to comprehend these environments, which can take years, if not decades, of research and testing. However, breakthroughs are continually emerging. Advances in observational technology, such as powerful telescopes and precise instruments, have allowed scientists to gather data from unreachable locations. For example, the first ever image of a black hole's shadow, captured by a global network of radio telescopes, marked a monumental step in our understanding of these enigmatic objects. Similarly, experiments conducted in particle accelerators that recreate conditions similar to those of the universe's infancy have opened a window into the forces that shaped our cosmos. Furthermore, interdisciplinary collaboration between astronomers, physicists, and engineers has accelerated progress in solving these puzzles. As various fields merge, new approaches and ideas flow, creating innovative methods to tackle age-old questions. The shared goal of uncovering the mysteries of the universe unites scientists, driving them to overcome both obstacles and limitations in unprecedented ways. This quest is ongoing, and each discovery paves the way for further exploration in the ever-evolving landscape of cosmic science. In a universe where the accumulation of knowledge is viewed differently, we might see a more profound connection between beings and their environment. Imagine if every discovery made by one individual was instantly shared with everyone else, rather than needing time and effort for information to spread. This could create an atmosphere where learning is not as isolated or fragmented, enhancing collective understanding rapidly. In such a scenario, concepts might build on each other much faster than in our current reality. When someone in this universe learns something new, that knowledge might ripple outwards immediately, like a stone tossed into still water, sending waves of understanding to every corner of society. Instead of slowly progressing through trial and error, innovations could happen simultaneously across vast distances, leading to breakthroughs at an astounding pace. On the other hand, with immediate knowledge sharing, there could be benefits as well as drawbacks. While collaboration might fuel progress, the lack of independent exploration could stifle creativity. Instead of unique perspectives and diverse paths of thought, ideas may converge too quickly, leading to a more homogeneous understanding of the universe. Members of this universe could potentially perceive reality in richer, more complex ways by collaborating continuously. Their discussions could evolve simultaneously, leading to a multidimensional grasp of existence that our current understanding struggles to achieve, locked in a linear progression of learning. The balance between rapid knowledge sharing and the depth of individual exploration would significantly shape the nature of their intellectual landscape. As humanity looks to the stars, the development of communication technologies capable of bridging vast cosmic distances becomes more vital than ever. Currently, our best forms of communication rely on radio waves, which are excellent for sending signals across space, but encounter limitations as the distance increases. Imagine trying to send a message across a lake. The further away your friend is, the softer your voice becomes. To overcome these challenges, new technologies are being explored. One of these advancements includes laser-based communication. Unlike radio waves which spread out, lasers can send focused beams of light that travel long distances without losing strength. This could allow for clearer and faster communication between spacecraft and Earth. It is like using a flashlight to shine a message through the darkness instead of shouting across a wide space. Another promising area is quantum communication. This technology uses the principles of quantum mechanics to send information in a way that is inherently secure and incredibly fast. Picture it as a magical coin toss where two people flip their coins, and instantly they know whether their coins show heads or tails, no matter how far apart they are. This could mean that messages sent across light years could arrive simultaneously, opening doors for real-time communication with space probes or future colonies on distant planets. Moreover, utilizing satellite networks is an essential step in improving communication over vast distances. By creating a constellation of satellites, signals can bounce between them, providing a more stable connection even for far-reaching spacecraft. It's similar to using a series of mirrors to direct sunlight to a specific point, ensuring the message reaches its destination effectively. As we delve deeper into the cosmos, the integration of artificial intelligence could streamline communication efforts as well. AI could manage data, filter noise, and prioritize signals, ensuring that essential information is processed swiftly, much like a librarian sorting books efficiently to keep the information flowing without delay. In the pursuit of bridging these cosmic distances, not only do we foster connection, but we expand our understanding of the universe. Each technological breakthrough holds the potential to unlock secrets of distant worlds, making our dreams of interstellar communication a reality. The journey may be long, but the path forward is filled with incredible possibilities. Imagine a universe where traditional methods of communication, like speaking or sending signals, might not be suitable for the vast distances between stars and galaxies. In such a scenario, innovative approaches would likely emerge. One possibility is the use of light pulses, akin to flashes of a flashlight. This method would involve encoding messages in patterns of light and sending them across space. Laser technology could make this very effective, sending beams to distant spacecraft or civilizations, but it would require precise alignment to ensure the signal reaches its destination. Another intriguing method could be the use of gravitational waves. These ripples in space-time are created by massive objects moving in space, such as merging black holes or neutron stars. If we could develop the technology to encode information onto these waves, it could create a unique communication channel that travels through the fabric of the universe, able to bypass obstacles that may block other types of signals. Additionally, there's the concept of using quantum entanglement, a phenomenon where pairs of particles become linked, affecting each other instantly regardless of distance. This could allow for instantaneous communication across enormous expanses. Although still theoretical, harnessing this effect might lead to a way to send messages in real time, defying the limits of light-speed travel. Finally, advanced civilizations may also rely on biosignals or chemical signals, which could include sending encoded messages through genetically modified organisms or even specialized synthetic entities. These biocommunication methods could work in environments where electronic signals struggle, opening new horizons for interaction with alien life forms. In this expansive universe, communication methods would likely depend on the unique characteristics of the sender and receiver, the environment they exist in, and the technology they develop, leading to a remarkable variety of ways to connect across the cosmos. Technologies play a crucial role in shaping the way civilizations communicate, and they can both enhance and challenge intercivilizational dialogue. On one hand, advancements in communication technologies, such as the internet and satellite communication, enable instant connections across vast distances. Imagine two distant planets engaged in a conversation. These technologies facilitate real-time interactions, allowing for the exchange of ideas, cultural practices, and knowledge. This can lead to greater understanding and cooperation among civilizations as they share experiences and learn from each other's advancements. However, there is a flip side to these technological benefits. While they can create opportunities for dialogue, they can also pose significant challenges. For instance, differences in technological access can lead to imbalances in communication power. If one civilization has advanced technologies while another lags behind, it may struggle to participate fully in discussions. This disparity could foster misunderstandings, as the more advanced civilization may unintentionally dominate conversations or misinterpret the values of the less advanced one. Additionally, the very nature of technology can create barriers. Cultural differences may influence how civilizations use communication tools, leading to conflicts or misinterpretations. A message that is clear in one context could be seen completely differently in another. The speed at which information travels can also create issues, as rapid exchanges may prevent thoughtful dialogue, leading to rushed conclusions that do not account for deeper meanings or traditions. Ultimately, for intercivilizational dialogue to thrive, there must be efforts to ensure equitable access to technology and a mutual willingness to understand and adapt to different communication styles. This balancing act could harness technology's potential while minimizing its disruptive effects, fostering a rich tapestry of intercivilizational exchanges. In a hotter universe, the concept of cosmic prediction or divination could take on profound new meanings. As the universe expands and evolves, conditions change significantly. Greater temperatures may lead to more chaotic environments where established patterns could become unpredictable. In such a setting, ancient practices of seeking patterns or insights from the cosmos might find a burgeoning relevance as people yearn for stability amidst uncertainty. Historically, celestial bodies have guided human understanding of seasons, tides, and agricultural cycles. In a hotter universe, the change in climatic conditions could influence these cycles, prompting societies to look to the stars for answers to navigate the unpredictable fluctuations. This practice could evolve into a modern form of cosmic divination, where scientists and thinkers analyze celestial patterns not just for navigation or agriculture, but to anticipate broader ecological shifts and to understand the universe's deeper mysteries. This heightened significance might also reflect a psychological need for connection in a rapidly changing world. Just as astrology offered comfort in turbulent times, a scientific or philosophical interpretation of cosmic events would serve as a compass for humanity's place in the cosmos. People might cling to the idea of harnessing cosmic phenomena to find meaning or predict future events, seeking a semblance of control over their lives amid warming climates and shifting environments. Ultimately, as our understanding of cosmic forces deepens, the intersection of science and spirituality could emerge with greater intensity. The desire to predict and interpret beyond empirical data might become a fundamental way for societies to cope with and understand the complexities of a hotter universe, making divination an intriguing blend of science, hope, and human intuition. Throughout history, people have often looked to the stars and planets for guidance, believing that cosmic influences could shape their lives. As our understanding of astronomy evolves, some mystic or occult practices may gain new prominence based on these perceived celestial connections. One notable practice is astrology, which interprets the positions of celestial bodies to offer insights into personal traits and future events. As interest in space increases, people might turn to astrology seeking to understand their place in the universe. With each planetary alignment and celestial events such as eclipses or conjunctions, practitioners may highlight how these occurrences can affect human behavior and emotions, appealing to individuals looking for answers in an ever-changing world. Another area that could see growth is cosmic ritual practices. Many existing traditions already incorporate lunar phases or planetary cycles to guide rituals and meditations. As our awareness of cosmic phenomena expands, Practitioners may create new rituals that synchronize with significant astronomical events, such as supermoons or meteor showers. These moments could be seen as powerful times for personal reflection or collective intention setting, enhancing the connection to the universe. Additionally, the rise of mindfulness and holistic wellness could intertwine with these cosmic practices. People might integrate techniques such as guided meditations focused on cosmic energy, or ceremonies that honor the universe's rhythms, aimed at promoting inner peace and balance. This blend emphasizes a deeper connection between personal well-being and the vastness of the cosmos. Overall, as society continues to grapple with the mysteries of the universe, mystic practices rooted in cosmic influences may resonate more strongly. They often provide individuals with a sense of purpose, belonging, and connection to something greater, making them relevant as people seek answers beyond the everyday. The intersection of scientific and mystical methods of predicting the future presents a fascinating landscape where both perspectives can coexist or clash. Science relies on observable evidence and repeatable experiments to generate knowledge. It seeks to understand the world through rigorous inquiry, focusing on natural laws that govern everything from the motion of planets to the behaviors of subatomic particles. When scientists make predictions about the future, they base them on data, patterns, and rigorous calculations. For instance, meteorologists use vast amounts of data to create weather forecasts that, while not perfect, rely on established principles of atmospheric science. On the other hand, mystical methods often draw from intuition, spirituality, and ancient traditions. They include practices such as astrology, divination, and various forms of prophecy. These approaches are less about measurable outcomes and more about personal insights or spiritual guidance. They often focus on a holistic understanding of life and the universe, relying on the belief that there are unseen forces that can influence future events. The two methods may coexist when individuals find value in both. Some people might appreciate scientific forecasts for their practicality, while also seeking mystical insights that provide personal meaning or spiritual comfort. This duality can lead to a richer understanding of existence, as science explains the how of the universe, while mystical practices address the why. However, conflict arises when mystical predictions make claims about the future that can be tested scientifically. For example, if an astrological forecast suggests a specific event will happen, it may collide with scientific explanations that account for the same event. Ultimately, the relationship between these two perspectives often hinges on the understanding and openness of individuals. Recognizing that they serve different purposes, science seeks to uncover empirical truths, while mystical methods pursue spiritual understanding, can allow for a dialogue rather than a dispute. Both approaches can offer unique insights, contributing to a more nuanced view of the future and our place in the cosmos. In a hotter universe, the dynamics of alliances would change significantly due to the increasing challenges posed by higher temperatures and altered environmental conditions. Under such stress, resources like water and energy would become scarcer, pushing civilizations to compete more fiercely for survival. Initially, alliances may form among civilizations that recognize the need to share resources and knowledge to combat the common threat of rising temperatures. These partnerships could lead to greater cooperation in technology sharing and strategies for efficient energy use. For instance, two societies might work together to develop advanced cooling technologies, benefiting both in their struggle against heat. However, as conditions worsen and resources dwindle, the very alliances that formed out of necessity could unravel. Trust might erode when one partner appears to hoard resources or fails to meet their commitments. The desperation caused by extreme heat could lead to suspicion and rivalry, causing once cooperative groups to fracture. New alliances may emerge as groups shift their focus to more favorable partners, believing they can secure better resources or protection. In this scenario, smaller, more agile factions could form, adapting quickly to the rapid changes and often seeking alliances based on current needs rather than long-term stability. Ultimately, the climate's harsh realities would not just test the strength of these alliances, but also shape the nature of relationships in a hotter universe. A constant need for adaptation and reassessment would dominate interactions, creating a complex web where trust, competition, and collaboration constantly intertwine. Imagining cosmic warfare opens the door to a fascinating discussion about how different environments in space could influence tactics and strategies. In the vastness of space, conditions are quite different from those on Earth. There is no atmosphere, which means sound cannot travel, and visibility can be limited by dust, asteroids, and the radiation from stars. If we consider conflict occurring in space, one of the most significant factors would be the vast distances between celestial bodies. Instead of engaging in close-range combat, spacecraft might rely on long-range tactics, using advanced targeting systems to strike from greater distances. This could resemble a game of chess, where players anticipate moves far ahead rather than reacting in the moment. The use of gravitational forces also would be a critical consideration. Spacecraft could maneuver using the gravity of planets or moons to gain speed or change direction, effectively using them as weapons or shields. By understanding how objects in space interact gravitationally, spacecraft could execute surprise maneuvers, making it difficult for opponents to predict their movements. Another factor is the potential for new technologies that harness the unique elements of space. Weapons could include directed energy beams or other futuristic armaments that utilize solar power or other sources. These tactics would need to take into account the intense energy fluctuations found in space, as well as shielding against cosmic radiation. Additionally, the psychological aspect of cosmic warfare would evolve as well. With solitary vastness, the challenge might not only be about physical confrontations, but also about manipulating communication. This means using misinformation to mislead opponents about one's true position or intentions, much like tactics employed in traditional warfare, but amplified by the vastness and isolation of space. Ultimately, cosmic warfare could indeed take on new forms and tactics as technology advances and our understanding of the universe deepens. This evolution would reflect the dynamic interaction between strategy, environment, and technology, paving the way for an entirely new arena of conflict. As we look towards the future of space exploration and utilization, the idea of peacekeeping strategies to maintain cosmic harmony becomes increasingly vital. In the vastness of space, the potential for conflict rises, especially as more nations and private entities venture into territories that were once unclaimed. One of the primary strategies could involve establishing international treaties to govern outer space activities. These treaties would set clear rules for all participants, focusing on shared uses and responsibilities, ensuring that activities such as satellite launches, space mining, and exploration do not infringe on the rights of others. Another approach could involve creating a unified space governance body made up of representatives from various countries and organizations. This body would operate similarly to how the United Nations functions on Earth, mediating disputes and fostering cooperation. The goal would be to promote dialogue over conflict, encouraging nations to work together on mutual challenges like space debris management or planetary defense against asteroids. Moreover, technology can play a critical role in maintaining peace. Developing transparent systems for tracking space activities like satellite positions and orbital paths would allow all players to monitor each other's actions and avoid unwanted collisions. This kind of accountability could prevent misunderstandings that might lead to tensions. Additionally, educational programs aimed at cultivating a culture of collaboration and respect for the shared nature of outer space are essential. By fostering a sense of stewardship, current and future generations can learn the importance of working together rather than competing for resources in space. Ultimately, maintaining cosmic harmony will require a combination of diplomacy, effective governance, cutting-edge technology, and a shared commitment to peaceful exploration. Through collective efforts, we can ensure that the cosmos remains a realm of discovery rather than a theater of conflict. To grasp how a slight increase in heat during the birth of the universe could shape our reality, imagine the beginning as a monumental explosion called the Big Bang. This event created all the energy and matter that exists today. Now, if that initial explosion had a fraction more heat, the universe would have expanded and cooled differently. In this hotter scenario, particles like protons and neutrons would have had more energy. This could have led to different phases of matter, and even allowed heavier elements to form more readily in the early universe. These changes would heavily influence the type of stars that later formed, the elements they produced, and consequently, the kinds of planets that emerged. If the early universe had a higher temperature, It could mean that stars might burn hotter and brighter, but have shorter lifespans. These scorching stars would explode in supernovae, creating a higher abundance of diverse elements, but potentially altering the chemical pathways leading to the complex atoms that make up life as we know it. In a reality shaped by this higher heat, galaxies may also take different shapes and sizes. The gravitational forces and interactions would play out uniquely, potentially resulting in varying structures across the universe. The very conditions on planets could transform as well. Perhaps they might be too hot for liquid water or possess environments entirely unlike Earth. Ultimately, an increase in initial temperature would not just tweak the fabric of stars and galaxies, it would change the fundamental rules governing life itself. Thus, our understanding of reality hinges on these early moments, showing how fragile our existence is contingent on specific cosmic conditions. The idea of alternate universe structures opens up a landscape filled with philosophical and scientific possibilities. First, on a scientific level, the concept invites us to rethink the nature of reality itself. If alternate universes exist, each with its own unique laws of physics or versions of history, it challenges our understanding of what is possible. Science could evolve to incorporate new theories like multidimensional contexts where these universes exist side by side. Researchers may explore how quantum mechanics applies across these realms, leading to groundbreaking revelations about existence and consciousness. Philosophically, this notion raises profound questions about identity and choice. If every decision creates a new universe, what does that mean for free will? Every action could lead to a branching path, making individuals ponder the significance of their choices. This can lead to new ethical frameworks where actions are evaluated not solely on their immediate impact, but also on the multitude of outcomes that unfold. Additionally, the concept might ignite debates about the nature of existence itself. Are these alternate universes as real as our own, or merely speculative constructs? This duality offers fertile ground for existential inquiry. Such discussions could profoundly influence cultural and spiritual views, shaping beliefs about destiny, fate, and the universe's overarching design. The exploration of alternate universe structures not only challenges scientific paradigms, but also provokes deep philosophical introspection. It encourages a re-evaluation of our perceptions, inviting us to ponder our place within a potentially infinite cosmos. The boundaries of what we perceive as possible are continuously evolving. In many ways, our imagination acts as a bridge to new realities. Over history, people have dreamed of concepts that once seemed impossible, like flight or communication across vast distances. Each time we push the frontiers of our understanding, imaginative ideas become grounded in scientific achievement, transforming what once felt like fantasy into reality. Consider the advancements in technology that have emerged from human creativity. The internet, smartphones, and space exploration began as ideas that existed in the minds of innovators. These breakthroughs expand our perceptions, showing us that limits are often self-imposed or based on the knowledge available at any given time. When we explore space, we encounter phenomena that challenge our understanding, prompting us to reconsider what is achievable. Concepts like colonizing other planets or harnessing energy from stars become topics of serious discussion rather than distant dreams. As our understanding of physics and biology grows, so too does our capacity to imagine solutions to problems that seem insurmountable today. Moreover, the collective curiosity of humanity sparks innovation. By sharing ideas, we break down barriers and enter realms previously thought to be beyond our grasp. This communal imagination fosters an environment where what was once inconceivable can gradually become plausible. Our perception of possibility is a reflection of our willingness to explore the unknown and to challenge the status quo. As we evolve, so too will our capability to push the boundaries of imagination and reality. In a universe where the origin of heat is fundamentally different, art and symbolism would likely undergo remarkable transformations. To grasp this, consider how heat influences life and conditions on our planet. Heat is crucial for everything from how planets form to the existence of life itself. If this foundational aspect were altered, perhaps by a different type of star or unique cosmic events, it could radically change our reality. Artists often draw inspiration from their environment, using symbols that represent their daily experiences, emotions, and cultures. In a universe with an altered heat origin, the natural world might appear unique, leading to entirely new forms of expression. For example, if certain landscapes were dominated by vibrant colors born from unusual heat patterns, artists could incorporate these vivid hues in their works. Instead of a palette grounded in familiar blues and greens, they might turn to unforeseen shades that convey a sense of otherworldliness. Furthermore, symbolism might evolve to reflect the new relationships between beings and their surroundings. If this altered heat source brought about different cycles of life or unconventional natural rhythms, symbols within art could depict balance and disruption in innovative ways. For instance, motifs that traditionally symbolize growth and decay might merge or even flip, showing how life might flourish under unexpected conditions or adapt to survive in a harsher reality. This exploration of art in such a transformed universe would not only serve as a reflection of external conditions, but also a mirror to the shifting human experience. People's understanding of life, existence, and their place in the cosmos would likely be redefined. The narratives told through art could illustrate resilience, adaptation, and the search for meaning in an extraordinary reality. As a result, art would document not just the beauty or challenges of this new universe, but the profound shifts in thought and culture it precipitates. As humanity continues to explore the vastness of the universe, we can anticipate new artistic motifs and styles influenced by celestial phenomena and the mysteries that lie beyond our planet. Space itself offers a wealth of inspiration, beginning with the stunning colors and patterns seen in the cosmos. Artists may be compelled to embrace the vibrant hues of distant nebulae, combining iridescent colors to convey an otherworldly experience that transcends traditional palettes. Additionally, the concept of time and its relativity could spawn a unique style focused on movement and fluidity. Imagine artwork that gives a sense of time stretching or contracting, perhaps using abstract forms that seem to warp and bend, symbolizing the gravity wells created by celestial bodies. This approach would not only reflect the nature of time, but also invite viewers to experience the unpredictability of the universe in a visceral way. Incorporating technology into art will likely play a significant role as well. With advancements in virtual and augmented reality, artists can create immersive experiences that allow audiences to explore planets, starfields, or even simulated travel through wormholes. This fusion of art and technology could lead to new narrative forms, where viewers actively participate in their journey through the universe. Moreover, the idea of extraterrestrial landscapes could inspire a genre of cosmic realism. Artists may pursue a style that captures imagined yet scientifically plausible environments of alien worlds, incorporating unique features such as strange flora, unfamiliar geological formations, or alien atmospheres. These artistic depictions would push the boundaries of our imagination, encouraging discussions about life beyond Earth. Finally, themes of interconnectedness and unity may emerge, reflecting the idea that all things in the universe are intertwined. Artists might explore these concepts through collaborative works that blend different mediums, cultures, and perspectives, becoming a testament to our shared human experience in an endlessly expanding cosmos. This focus on collaboration would symbolize the collective curiosity that drives humanity's quest to understand the universe more deeply. Cosmic events and structures have long captivated artists and creators, inspiring a rich tapestry of visual and conceptual representations. One striking way to depict these vast phenomena is by translating complex scientific ideas into more relatable imagery. For instance, the explosive birth of a star can be captured through vibrant colors and swirling forms that suggest intense energy and transformation, evoking a sense of awe at the universe's power. Artists often draw on the scale of the cosmos to create a sense of wonder. A simple canvas might showcase an expansive night sky filled with swirling galaxies, each painted with careless strokes that evoke the endlessness of space. This technique not only illustrates the vastness of the universe, but also invites viewers to reflect on their place within it. Conceptually, such expressions can delve deeper, contemplating themes of time and existence. A visual might juxtapose images of cosmic phenomena, like supernovae or black holes, alongside human experiences like birth or decay, to explore the cyclical nature of life. This approach prompts viewers to consider how cosmic events mirror the human experience, creating a profound connection between the microscopic and the macroscopic. Moreover, modern technology has also revolutionized artistic representation. Digital art allows for dynamic visuals that can simulate the motion of celestial bodies or the dance of particles in space, embodying the energy inherent in cosmic events. These pieces can feel almost alive, embodying the ongoing changes in the universe beyond what is visible to the naked eye. In this way, artistic expressions of cosmic events not only aim to visually depict the grandeur of the universe, but also provoke thought and emotion, connecting the infinite to the intimate aspects of life. Such representations invite us to look upward and inward simultaneously, finding meaning in both the vast cosmos and our fleeting existence within it. The evolution of a universe that began ever so slightly hotter than our own hinges on the concepts of continuity and change. Continuity represents the unbroken chain of events and processes that shape cosmic structures, from the formation of simple particles to sprawling galaxies. Change emphasizes the transformation of these elements over vast expanses of time. In the early moments of the universe, when temperatures were extraordinarily high, fundamental particles like protons and neutrons formed in great abundance. If this initial heat had been even slightly greater, it would have influenced the balance of matter and energy crucial to later stages of development. For instance, a hotter start would have resulted in a more rapid fusion of these particles, potentially leading to a different balance between matter and antimatter. This shift could impact the creation of stars and galaxies, as a universe with altered density and energy would experience variation in gravity's pull. As the universe expands and cools, continuity ensures that the laws of physics remain consistent. These laws guide the formation of complex structures and reactions in the cosmos. However, change allows us to see how a slightly hotter beginning could alter the timeline of cosmic evolution. Galaxies might grow larger due to accelerated star formation rates, or black holes may emerge earlier and evolve differently due to the varying environmental conditions. Thus, the modest difference in temperature at the universe's birth can cascade into significant evolutionary changes. While continuity provides a framework where processes unfold predictably, change introduces unexpected twists, resulting in a universe that could be markedly different from the one we inhabit today. The interplay between these two forces, then, is central to understanding how varied cosmic landscapes can emerge from seemingly minor initial conditions. Throughout the ages, the universe has shown us patterns and cycles that repeat over vast stretches of time. These cyclical events, like the birth and death of stars, the formation of galaxies, or the changing of cosmic seasons, offer a rhythm to the universe's story. Just as the seasons on Earth transform landscapes, the universe undergoes its own transformations, revealing new beginnings from the remnants of the old. This cycle of creation and destruction suggests that every end may lead to a new beginning, essential for the evolving tapestry of existence. Additionally, innovative breakthroughs in our understanding of the universe have the power to reshape this narrative in profound ways. As humans venture further into space and refine our technologies, each discovery can open doors that redefine our comprehension of cosmic phenomena. Imagine the implications of discovering new forms of energy that could fuel spaceships for longer journeys, or breakthroughs in understanding dark matter, which could reveal hidden aspects of the cosmos. Each advancement not only enhances our knowledge, but also adds chapters to the grand story of celestial evolution. Over an eternity, these cycles of renewal and leaps in knowledge create a dynamic conversation between what was, what is, and what could be. They invite speculation and exploration, encouraging civilizations, whether on Earth or elsewhere, to dream bigger and reach further. With every breakthrough, we find ourselves not only rewriting our own destiny, but also reimagining our place within this vast, ever-unfolding universe. The rich interplay between cyclical nature and innovative thought illustrates a universe that is not static, but a living, breathing entity constantly evolving toward new horizons.